What if I told you that time isn't what you think it is? That the very sensation of before and after might just be a trick of the universe, a fragile illusion propped up by something we can't touch, can't see, but feel every second of our lives. You know it as time. But what if time doesn't actually flow? What if everything you know about yesterday leading to today, and today becoming tomorrow, is simply a story told by the deepest laws of physics, and that story is written not in minutes or hours, but in entropy? But before we continue, subscribe to the channel so you don't miss out on any of these videos. Right now, somewhere in the vast darkness of space, a dying star is collapsing into a black hole. Time, there, is stretching and warping. In another corner of the universe, a drop of ink disperses in a glass of water, a simple act, but one that carries the signature of time's relentless arrow. And here you are, wondering why you can remember the past but not the future. That question alone cracks open the door to one of the most profound mysteries of existence. This is the arrow of time. And it's not just about clocks ticking. It's about why you age. Why your coffee cools. Why we can remember being children but not old men. It's about how the universe began, and possibly, how it will end. It's about how everything, from your thoughts to the fate of galaxies, is bound to an invisible gradient that stretches from order to chaos. But here's where it gets even stranger. The fundamental laws of physics don't care about time. They run just as easily forward as backward. In the equations that govern reality, from Newton to Schrödinger, time isn't a river. It's a dimension, like space. Yet, everything we know, everything we feel, screams otherwise. So why? Why do we feel time going one way? Why can we destroy but not undestroy? Why can a vase fall and shatter, but never spontaneously leap back onto the table, shards reforming, dust lifting back into shape? The answer lies in a single, haunting word, entropy. And that's where our journey begins. To understand time, really understand it, we have to plunge deep into the strange and slippery concept of entropy. It's not just about disorder. It's about probability, information, memory, and even consciousness. Entropy is the thread that connects the microscopic laws of atoms to the grand tapestry of the universe. It is the unseen hand pushing every event, every breath, every star toward a future that is statistically more likely, not more meaningful, not more dramatic, just more likely. In this video, we're going to stretch your mind. We'll dive into black holes, peer into the early moments of the Big Bang, wrestle with Boltzmann's brain, confront the heat-death of the universe, and ask, is time real? Or is it just the story entropy tells us? So buckle in. Because by the end of this journey, you might not think of time the same way again. Let's begin. The arrow of time. It sounds poetic, something you might read in a science fiction novel. But in physics, it's a real concept. And yet, it's weirdly elusive. Let's start with something that might surprise you. Most of the laws that govern the universe don't care about the direction of time. Imagine you film two particles bouncing off each other in a vacuum. Play that video in reverse, and you wouldn't be able to tell which is forward and which is backward. The equations of motion, whether Newton's classical laws or the probabilistic dance of quantum mechanics, are time-symmetric. They work both ways. But our world isn't like that, is it? You spill a glass of water, you can't unspill it. You burn wood, you can't unburn it. You age, and you don't get younger. There's a glaring difference between past and future. So what gives? Enter Ludwig Boltzmann, the 19th century physicist who dared to look deeper. He realized that while the microscopic rules of particles don't prefer a direction in time, the statistical behavior of many particles, systems with billions upon billions of components, does. And this behavior can be described with a quantity he called entropy. Entropy is often misunderstood as disorder, but that's not quite right. It's better to think of it as the number of possible microscopic configurations a system can be in while still looking the same from a macro perspective. Imagine a deck of cards. You shuffle it, that's high entropy. You arrange it by suit and number, that's low entropy. There are way more shuffled configurations than ordered ones. So if you close your eyes and randomly rearrange the cards, you're far more likely to get a high entropy result. That's the heart of the arrow of time. Not some cosmic clock ticking. Not some metaphysical force pulling us forward. It's just probability. The universe moves from less likely states to more likely ones, from low entropy to high. But this brings us to a weird realization. If entropy is all about probabilities, then our perception of time is just about what's likely. And that means that the future, the one we think is unwritten, might not be as open as we believe. It's just more likely to be messy, random, and irreversible. But wait. If entropy always increases, why was the universe ever in a low entropy state to begin with? Now that is the puzzle. You see, the early universe, right after the Big Bang, was surprisingly ordered. It was hot, dense, but smooth. Very low entropy. That's the opposite of what you might expect. If entropy increases over time, why didn't the universe start out in chaos? This is called the past hypothesis. And it's one of the biggest unsolved mysteries in physics. Because for the arrow of time to exist, for there to be a direction, you need a starting point of low entropy. It's like dropping a ball at the top of a hill. It rolls downward because it started high. But we don't know why the universe started at the top. Some theories suggest it was a quantum fluctuation. Others propose our universe is part of a multiverse, and we just happen to live in a bubble where time behaves this way. Some scientists think we might be part of a cyclic universe, where entropy resets in strange ways. But no one knows for sure. What we do know is that the arrow of time, as we experience it, depends on this low entropy beginning. And without it, the universe would be frozen in a statistical fog, with no past, no future, no memory, no decay, no change. Now let's take a step back and think about what this means for us, as humans. Because entropy doesn't just govern the universe. It governs you. Your memories? They depend on entropy. You remember the past because it's the direction in which entropy increases. You forget the future because it hasn't happened, statistically speaking, and your brain is wired to record increasing entropy. In fact, every act of remembering increases entropy. Your brain, as it processes and stores information, releases heat. It burns energy. It adds to the chaos. Even thought is not free from the arrow of time. The arrow points forward because that's where the options are. That's where disorder grows. That's where information can be forgotten, scattered, lost. And yet, there are moments in physics where the arrow seems to flicker. Quantum mechanics introduces uncertainty and probability in a strange, delicate dance. Particles can be in superpositions, entangled across space and time. Some interpretations, like the transactional interpretation, even allow for backward causality, where events in the future influence the past. The delayed choice quantum eraser experiment bends our intuition further, suggesting that the measurement of a particle can affect its earlier state, or at least, how we interpret that state. But despite all these paradoxes, when we zoom out, the arrow returns. Entropy always wins on the large scale. And that's where the story gets darker. If entropy always increases, where does it lead? To the heat death of the universe. A state where entropy reaches a maximum. No more stars. No more motion. No more structure. Just a thin, cold fog of particles drifting in an eternal night. Everything, thoughts, galaxies, civilizations, erased in the uniformity of statistical equilibrium. But is that the end? Or is there more to time than entropy? Some scientists think the arrow of time is emergent, not fundamental. That time itself might be an illusion, a construct born from change, from information, from entropic gradients. Julian Barber proposes that time is simply change, that the universe is a collection of nows, and what we perceive as flow is just our brain linking these moments. Others look to black holes. Stephen Hawking showed that black holes aren't entirely black. They emit radiation, slowly evaporating over time. This process increases entropy, yes, but it also raises questions about information. What happens to the data that falls into a black hole? Is it lost forever? That would violate the principle of information conservation. So some physicists believe that information is somehow encoded in the event horizon, preserved in strange ways, leading to the holographic principle, a theory that suggests the universe is a kind of projection from a two-dimensional surface. Mind-bending stuff, right? And we're just getting started. We live in a world where time feels tangible. We experience it as something that flows, something that is always moving forward. We remember the past, and the future is something we can only imagine. The present is fleeting, a single moment that disappears almost as soon as we notice it. But this perception of time, our feeling of a constant flow, is at odds with what we know about the laws of physics. As we've seen, the laws of physics don't care about the direction of time in their fundamental equations. The microscopic world, governed by the same laws of physics that apply everywhere in the universe, works just as well if time is reversed. However, our experience of time is anything but symmetric. The second law of thermodynamics, the law that governs the direction of time, dictates that entropy in an isolated system can only increase. That's what gives us the arrow of time, the direction in which time seems to move. It's the reason why we can remember the past, but not the future. It's why things tend to get messy over time, why things decay and break down instead of spontaneously organizing into more complex structures. Now, let's take a step deeper into this. The very concept of entropy can be tricky, so let's break it down further. Imagine you have a room filled with gas particles. Initially, all the particles might be clustered in one corner. This state is low in entropy because there are fewer possible configurations, fewer ways the particles can be arranged in the room. Over time, the particles will spread out, moving and bouncing off each other in unpredictable ways. Eventually, the particles will fill the room in a more uniform distribution. This state is high in entropy, because there are many more possible configurations for the particles to be spread throughout the room. Now, let's apply this to our universe. The universe started in a very low entropy state, which is why time moves in one direction. The Big Bang itself was an event of incredibly low entropy, with a vast amount of matter and energy compressed into a tiny, highly ordered space. From there, entropy has been increasing ever since. Stars burn through their fuel, galaxies collide, and black holes form. Each of these processes increases entropy in its own way. But we also know that as entropy increases, things become more disordered, less organized. The universe is becoming less and less predictable, and that's part of why time feels like it moves in one direction. The question then becomes, what is the ultimate fate of the universe? If entropy continues to increase indefinitely, where does it all end? One possibility, as mentioned earlier, is the idea of heat death. This is the scenario in which the universe reaches a state of maximum entropy, where all energy is evenly distributed and no further work can be done. Stars burn out, black holes evaporate, and matter itself decays into a uniform soup of particles. There will be no more events, no more change, just a cold, lifeless universe where nothing happens. But there are alternative theories as well. Some physicists believe that the arrow of time might not be as irreversible as we think. There are speculative ideas such as the concept of a cyclic universe, where the universe goes through endless cycles of big bangs and big crunches. In this scenario, time doesn't have a singular endpoint but instead repeats, resetting itself in an eternal cycle. In this view, the arrow of time doesn't have to point toward heat death. Instead, it points toward a new beginning, a new Big Bang, and the process starts all over again. Another mind-bending possibility comes from quantum mechanics. In the microscopic world, things behave in ways that defy our common understanding of time. Quantum particles can exist in superpositions of states. They can be in multiple places at once or spin in multiple directions at the same time. When measured, however, these particles seem to choose one outcome, collapsing from a superposition into a definite state. This has led some physicists to wonder, could the fundamental nature of time itself be more flexible than we think? Could time in some sense be an illusion, created by our limited perspective on the world? This brings us to the concept of time symmetry in quantum mechanics. Time symmetry is the idea that the fundamental laws of physics are indifferent to the direction of time. Whether time moves forward or backward, the rules that govern the behavior of particles remain the same. But while this symmetry holds true at the microscopic level, we still experience time as a one-way street in our everyday lives. Why is that? The answer lies in entropy. The second law of thermodynamics doesn't apply to individual particles or even small systems. It's only when you look at large systems, systems with a vast number of particles, that the increase in entropy becomes statistically inevitable. The reason we experience time as moving forward is that the universe as a whole is a large system, and entropy is increasing in it. It's not just that time flows in one direction because of the second law, it's that the universe is a vast collection of systems, and the direction of time is set by the behavior of these systems. The mind-blowing implications of this idea go even further when we consider the role of entropy in the nature of life itself. Life is an incredible process of order amidst chaos. We are beings who thrive on maintaining low entropy states. Our bodies consume food, break it down into energy, and use that energy to organize atoms and molecules into highly ordered structures. But as we live, we also increase entropy in the world around us. We release heat, we produce waste, we generate disorder. And eventually, just like everything else in the universe, we age and decay. Our time is finite, and entropy dictates the rate at which we break down. From the moment we are born, entropy is on our side, working relentlessly to bring us back into the chaos from which we emerged. It's not just living things that follow this rule. The entire cosmos is bound to this law. From the birth of stars to their ultimate death as black holes, every event in the universe is shaped by entropy. And yet there are moments in the cosmos when entropy seems to behave in unusual ways. One of the most puzzling aspects of entropy is how it connects to the concept of information. In many ways, information is a measure of order, a way to describe the arrangement of matter in a particular system. But as entropy increases, information becomes harder to extract. The more disordered a system becomes, the less useful the information within it becomes. One of the most fascinating puzzles in this realm is the relationship between entropy and black holes. Black holes are regions of spacetime where gravity is so strong that not even light can escape. Anything that falls into a black hole, whether it's matter or information, seems to be lost forever. But this creates a problem. If information is truly lost, it would violate a fundamental principle of physics known as the principle of conservation of information. According to quantum mechanics, information about a system should never be lost, only transformed. But black holes seem to destroy information, creating a paradox that has baffled physicists for decades. This is where Hawking radiation comes into play. In the 1970s, Stephen Hawking proposed that black holes could slowly evaporate over time, emitting radiation in the form of particles. This radiation is now known as Hawking radiation, and it suggests that black holes are not entirely black. They gradually lose mass and energy, eventually disappearing entirely. The question, however, is what happens to the information that falls into a black hole? Does it truly vanish, or does it somehow escape through the radiation? This question leads us to a concept known as the holographic principle. The holographic principle suggests that the information about a volume of space can be encoded on its boundary, much like a hologram. If this is true, it would mean that all the information about the universe is stored at its edges, and that what we perceive as the interior of the universe is just a projection of that information. The idea is still highly speculative, but it could provide an answer to the black hole information paradox and give us new insights into the nature of time and entropy. As we ponder these cosmic mysteries, we are left with the fundamental question of whether time is a true, fundamental feature of the universe or just an emergent property. Time, as we experience it, seems to be intricately tied to the increase of entropy. But does time exist beyond that connection? Is it possible that time, like entropy, is a construct of the human mind, a way for us to make sense of the universe's deep, underlying laws? These questions continue to challenge scientists and philosophers alike. And while the answers remain elusive, one thing is clear: time is not just a measure of the passage of events, but a key to unlocking the deepest mysteries of the universe. The arrow of time points us toward the unknown, and in understanding its nature, we might one day understand the true nature of reality itself. The exploration of time and entropy raises profound philosophical and scientific questions about the very fabric of reality. While the physical processes that govern the universe are more or less well understood, the deeper implications of time's arrow leave us grappling with unresolved mysteries. The arrow of time is tied not just to thermodynamics and entropy, but also to the structure of the universe itself. One of the most significant features of our universe is that it's expanding. The Big Bang Theory describes how the universe began as a singularity, a point of infinite density and temperature. From that singularity, the universe began to expand rapidly in a moment known as the Big Bang. This expansion continues today, stretching space itself and carrying galaxies farther apart. This ongoing expansion seems to be linked to the arrow of time. In a static universe, where everything stays the same, there would be no distinction between past, present, and future. But because the universe is expanding, we see the passage of time marked by the movement of galaxies, the formation of stars, and the eventual cooling and spreading out of energy. In this sense, the increasing entropy of the universe is intrinsically connected to the expansion of space. As the universe continues to expand, it's not just space that's stretching. Time itself may be involved in this grand cosmic scale. The expansion could be interpreted as an extension of time, pushing forward the events that unfold in the cosmos. And yet, the expansion also complicates our understanding of time. As we look deeper into space, we look further back in time. Light from distant galaxies takes billions of years to reach us, meaning we're always observing the universe's past. This link between space and time, between the present and the distant past, underscores the idea that time isn't simply something that ticks away in a linear fashion. It's woven into the very structure of the universe itself. This deep connection between the expansion of the universe and the passage of time hints at the possibility that time, much like space, may have its own properties that are still to be discovered. Could time be more than just a dimension? Could it have layers and complexities that we've yet to unravel? It's this kind of question that pushes scientific inquiry forward, making us realize just how much we still don't understand about the universe. Moreover, the connection between entropy and time offers a clue about why the universe behaves the way it does. Entropy, as we've seen, is the driving force behind the arrow of time, and it's a measure of the disorder or randomness in a system. But why does the universe favor higher entropy over lower entropy? Why does the universe seem to move toward more disorder? And can we reverse this trend, or is it set in stone? The concept of reversing entropy, or at least halting its increase, is one of the most fascinating areas of thought in modern physics. Some theories suggest that there could be regions of the universe where entropy decreases, where localized order can arise. For example, life itself can be viewed as a system that defies the overall trend of entropy, maintaining complex, low-entropy structures over time by consuming energy from the environment. This idea of local entropy decreases in a broader context echoes the arrow of time, as entropy increases overall, but it also suggests that there may be ways to counteract entropy in specific circumstances. Perhaps one of the most curious aspects of entropy and the arrow of time is how it relates to consciousness. Consciousness seems to be intrinsically tied to our perception of time. We experience time as a continuous flow, and we have the ability to reflect on the past and imagine the future. This awareness of time passing allows us to make decisions, plan for the future, and understand the sequence of events in our lives. But how does this awareness connect to the fundamental laws of entropy? From a neurological standpoint, the brain is an incredibly complex system that organizes information, processes sensory input, and controls actions. It maintains a certain degree of order, using energy to sustain its functions. But the brain, like any other system in the universe, is subject to the laws of thermodynamics, and its processes are ultimately governed by entropy. The experience of time, then, may be a result of the brain's processing of information and the increasing entropy of the world around it. As we perceive the world, we build models of reality in our minds, using past experiences to predict future outcomes. This continual updating of mental models creates a sense of time moving forward. Interestingly, our perception of time is not always uniform. The way we experience time can vary depending on circumstances, emotions, and even the way our brains process information. In moments of intense focus, time seems to stretch. When we're bored or waiting for something, it seems to drag. In moments of excitement or fear, time might feel like it's speeding up. This subjective experience of time might be tied to the neuroprocesses involved in processing entropy, how our brains handle information and make sense of the world around us. This connection between entropy, the brain, and consciousness invites us to consider a new question. Could our understanding of time be influenced by our ability to perceive and interact with entropy? Could our subjective experience of time be a direct reflection of the increasing disorder in our surroundings? It's a question that hints at the very nature of reality itself. The nature of time and entropy is also deeply connected to another fundamental concept in physics, the concept of causality. Causality is the principle that events happen in a certain order, that causes precede their effects. This principle is essential to our understanding of time. It's why we can remember the past, but not the future, and why events in the universe seem to unfold in a certain sequence. The principle of causality underpins our understanding of everything from the motion of planets to the workings of everyday life. But it also ties into entropy. As entropy increases, systems become more disordered, and causality becomes less predictable. In a high-entropy state, the relationships between events become less clear. This increasing uncertainty is yet another feature of the arrow of time. The concept of entropy also helps us understand the concept of irreversibility, the fact that many processes in the universe are not reversible. For example, if you break a glass, you can't simply gather the pieces and restore it to its original state. This irreversibility is a direct consequence of the second law of thermodynamics. The glass's breakage represents an increase in entropy, and once that increase has occurred, it's nearly impossible to reverse the process. This reflects the fundamental nature of time. The events that have passed can't be undone, and the future is something we can't predict with absolute certainty. In some ways, the increasing entropy of the universe is what gives life its meaning. Without entropy, without the irreversible passage of time, there would be no change, no evolution, no movement. The very nature of life, with all its complexity and variety, is tied to the ongoing increase of entropy. As we experience time, as we live our lives, we are riding the wave of entropy, moving forward through time, creating and consuming energy, building and breaking down structures. And as the universe itself continues to age and entropy continues to increase, we are faced with the eventual end of everything. It's a sobering thought, but it's also a reminder of the preciousness of the time we have. The universe is destined to grow colder and more disordered, but while we're here, while we're alive, we experience the world in a way that is defined by change, by motion, by growth, and by decay. As we continue to explore the universe and our place in it, the arrow of time and entropy remain at the heart of the questions we seek to answer. Whether we're looking at the distant past, the present, or the future, time is always with us, always moving us forward, pushing us toward an uncertain end. Yet, in that forward march, we find the possibility for discovery, for learning, for understanding. Perhaps that's the greatest gift that time offers us, the ability to explore, to question, and to find meaning in the unfolding of events. Time and entropy are not just abstract concepts, they are the very essence of the universe itself, shaping the lives we live, the choices we make, and the future we can only dream of. The arrow of time points us toward the unknown, and it is in that unknown that we continue to search for answers, for understanding, and for the mysteries that lie just beyond the horizon. As we continue to probe deeper into the relationship between the arrow of time and entropy, we arrive at a critical point in our understanding of both. The concepts are not just theoretical, they have real-world consequences that influence everything from the heat-death of the universe to the mundane activities of our daily lives. We've seen how time and entropy are intricately linked on a cosmic scale, with entropy increasing as the universe expands and evolves. But this relationship also unfolds in more immediate, everyday contexts. From the moment we wake up to the moment we fall asleep, the passage of time is coupled with a relentless increase in entropy. At a microscopic level, every action we take is an exchange of energy and matter. When we eat, our bodies break down food into usable energy, increasing entropy in the process. Our cells take in nutrients, use them to perform various functions, and in doing so, release heat, another manifestation of entropy. This heat, the energy dispersed into the surroundings, is a small but constant reminder of the second law of thermodynamics, which dictates that no process can be entirely efficient. Some energy will always escape in the form of waste heat, leading to greater disorder in the system. This relentless increase in disorder is part of the very fabric of the universe, and it is precisely what makes life, with all its complexity and organization, so remarkable. The brain, the heart, the cells of the body, and all the other processes that sustain life are a continual battle against entropy. Living organisms are highly ordered systems that maintain their structure by importing energy from their surroundings. But even in these highly organized systems, entropy is always at work. The heat produced by metabolic processes, the wear and tear on molecular structures, and the eventual decay of biological organisms are all manifestations of entropy. The fact that living organisms can maintain a state of low entropy by harnessing energy is a remarkable aspect of the way time and entropy interact. Essentially, life thrives in an environment where time unfolds and entropy increases, but life itself is a temporary, localized decrease in entropy. This paradoxical relationship, that life depends on entropy but also pushes against it, is a testament to the delicate balance between order and disorder that defines our universe. But what happens when this balance is lost? When entropy takes over? The answer lies in the concept of the heat death of the universe, a future event where the universe has reached maximum entropy. This is the scenario where all energy has been evenly distributed across space, and no more work can be done. The stars will have burned out, the galaxies will drift apart, and there will be no energy left to sustain any meaningful processes. The universe will exist in a state of perfect equilibrium, with no gradients of energy to drive change or life. The idea of heat death may seem far off, almost inconceivably distant, but it's an inevitable consequence of the laws of thermodynamics. The arrow of time will continue to point in one direction, forward, until that final moment when all distinctions between past, present, and future collapse into a static, timeless existence. What does that mean for the future of time itself? If the universe reaches a state of maximum entropy, does time continue to exist in the same way it does now? Without any change, would time lose its meaning? These are questions that may never have definitive answers, but they challenge us to think about the nature of time and the universe in new and profound ways. As we approach the end of this exploration, it's essential to ask whether there are any other paths forward for time and entropy. Can we escape the inevitable increase in entropy, or is there a way to reverse the arrow of time? While the heat death of the universe is one possible outcome, there are other speculative theories that suggest different futures. One such idea is the concept of a big crunch, the possibility that the universe, after expanding for billions of years, might one day reverse course and collapse back in on itself. In this scenario, the increase in entropy would eventually lead to a cosmic contraction, where galaxies, stars, and planets collapse into a singularity. But how does this relate to time? If the universe were to collapse, would the arrow of time reverse? Would we witness a reversal of entropy, as everything implodes into a singular point, and time itself moves backward? This concept is far from certain, and it presents its own paradoxes. Reversing entropy would suggest a universe where causes precede effects, and the idea of time running backward is at odds with our current understanding of physics. Nevertheless, the Big Crunch remains one of the most fascinating alternatives to the heat-death theory, offering a different perspective on the fate of the universe and the ultimate direction of time. Another speculative idea involves the possibility of time loops, or closed time-like curves. These are theoretical constructs in which time could loop back on itself, creating a cyclical model where events repeat endlessly. In such a universe, the concept of entropy might take on a new meaning, as the increase in disorder could be balanced by the eventual return to a previous state. This model, however, faces significant challenges within the framework of our current understanding of physics, particularly when considering the nature of causality and the second law of thermodynamics. But like many speculative ideas in physics, it serves as a tantalizing glimpse into the possibilities that remain unexplored in the universe. As we stand at the crossroads of these grand cosmological theories, the relationship between entropy and the arrow of time remains a central mystery. Whether we're looking at the distant past, the present moment, or the uncertain future, time continues to move forward, pulling everything with it. Entropy, as the ever-present force driving that movement, shapes our universe, our lives, and even our very perception of reality. It's a force that defines the limits of what we can know, but it also opens the door to endless possibilities. The pursuit of knowledge about time and entropy is one of the most profound intellectual endeavors humanity can undertake. It challenges us to think about the universe in ways that go beyond our immediate experiences, urging us to contemplate the ultimate fate of everything that exists. Time, like entropy, is an enigma, a concept that seems simple on the surface but is infinitely deep when we examine it closely. Whether through the lens of thermodynamics, cosmology, or the subjective experience of human life, time and entropy shape the universe in ways that are both mysterious and awe-inspiring. Our understanding of time and entropy is still in its infancy. Theories continue to evolve, and new discoveries may shed light on the darkest corners of the cosmos. But the questions remain the same. What is time? What is the ultimate direction of the arrow of time? And how does entropy shape the future of the universe and our understanding of reality itself? As we continue to explore these mysteries, we can only wonder where the journey will take us. Will we unlock the secrets of time? Will we ever find a way to reverse entropy or understand the ultimate fate of the universe? Only time will tell, and perhaps, in the end, time itself will be the greatest mystery of all. Life resists entropy temporarily, but it can never escape it. From the moment a living system is born, it begins a slow but inevitable dance with disorder. Aging, disease, and death are not just biological events, they are entropic consequences. The body becomes less efficient at repairing itself, molecular systems begin to degrade, and complexity gives way to chaos. This is the thermodynamic cost of being alive. But while entropy is often associated with decay and disorder, it's not inherently destructive. It's simply a measure of the number of possible microstates a system can occupy. The more possibilities, the higher the entropy. It's a statistical measure, not a force or a malevolent agent. Entropy doesn't destroy, it transforms. A shattered glass, for example, has higher entropy than a whole one, not because something broke it in a malicious sense, but because there are more disordered arrangements of glass shards than there are orderly arrangements of an intact glass. Understanding entropy in this way reframes how we see the arrow of time. Rather than something that drags us toward ruin, it is the statistical trend toward probability. The universe evolves toward states that are more probable, not because it has a goal, but because that's what the math of large numbers dictates. The arrow of time exists because the future holds more probable, more entropic configurations than the past. This also explains why we don't see broken glasses spontaneously reassembling, or ashes reforming into logs. These aren't impossible events, they're just unimaginably improbable. The number of microstates that correspond to a pile of ash is vastly greater than those corresponding to a perfectly structured log of wood. So while physics doesn't forbid these reversals, entropy all but ensures they won't happen within the lifetime of the universe. And this brings us to a profound realization. The past is special not because of anything magical, but because it began in a highly ordered state. The early universe, just moments after the Big Bang, had extraordinarily low entropy. This is the key to why we experience time as moving in one direction. The low entropy beginning provides a reference point from which entropy can increase. Without this, there would be no arrow of time, no thermodynamic drive toward disorder, and no sense of the past being different from the future. But why was the early universe so low in entropy? This is one of the great unanswered questions in physics and cosmology. According to the second law of thermodynamics, systems evolve from low entropy to high entropy. So if the universe began in a low entropy state, that means it was extraordinarily special, an incredibly precise arrangement of matter and energy that defies easy explanation. Some theorists suggest that this special beginning might be a product of a deeper law of nature we have yet to uncover. Others speculate that the universe may be part of a multiverse, an ensemble of universes, each with its own laws and initial conditions. In this framework, our universe's low entropy might simply be a rare fluctuation in a much larger sea of entropy. It's a possibility, though still speculative. Roger Penrose, one of the great thinkers of modern physics, has proposed a concept known as the Weyl curvature hypothesis. In simple terms, it suggests that the early universe's low entropy was due to the geometric simplicity of spacetime at the Big Bang. According to Penrose, the initial singularity had extremely low gravitational entropy. As the universe expanded and structure formed, stars, galaxies, black holes, gravitational entropy increased. Black holes, in particular, are thought to be the most entropic objects in the universe, possessing vast amounts of entropy encoded on their event horizons. This interplay between matter, energy, and gravity reveals just how deeply entropy is woven into the story of time. Every galaxy that forms, every star that burns out, every atom that decays, they're all pieces of the universe's long, slow drift toward higher entropy. Even human consciousness is not immune to this grand entropic journey. Our memories, thoughts, and perceptions are all encoded in the physical structures of the brain. When we remember something, we change the arrangement of neurons and synapses, which consumes energy and produces heat, again, increasing entropy. Memory itself, then, is a function of entropy. We remember the past because it was more ordered than the present. We forget the future because it hasn't happened, and because it's probabilistically uncertain. This relationship between memory and entropy is a window into one of the most haunting truths of all. Our very sense of self, our awareness of time and identity, is entangled with the second law of thermodynamics. Who we are, the continuous thread of consciousness we call a person, exists because time has a direction. If entropy did not increase, if time were symmetrical, our minds might not be able to function. Cause and effect would blur. Experience would dissolve. And yet, as the arrow of time continues its relentless march forward, we are left to ponder the ultimate fate of the universe. If entropy must always increase, what happens when it reaches its maximum? This question leads us to one of the most sobering concepts in cosmology, the heat-death of the universe. So while physics doesn't forbid these reversals, entropy all but ensures they won't happen in any observable time frame. This is the essence of the arrow of time. The laws of physics are time-symmetric. They don't care whether time moves forward or backward. But entropy breaks that symmetry. It gives time a preferred direction, from low entropy to high entropy, and in doing so, it defines the past as different from the future. This leads us to one of the most fascinating puzzles in physics. If the fundamental laws are time-symmetric, why does entropy have a direction at all? Why did the universe begin in such an extraordinarily low entropy state? The early universe, just after the Big Bang, was remarkably uniform, smooth, and ordered, a condition that defies our expectations based on entropy. Given the chaotic nature of energy and particles, we would expect the universe to have started in a high entropy state. But it didn't. It began in a very special configuration, one that allowed for the gradual increase of entropy over billions of years. This low entropy beginning is a mystery that has yet to be fully explained. Some physicists suggest that it's simply a brute fact, a boundary condition of our universe that must be accepted. Others propose more complex models, like the multiverse theory, where our universe is just one of many, and ours happens to be the one that began with low entropy. In such scenarios, our universe is part of a vast ensemble of universes, each with different initial conditions. Most might be dead and entropic from the start, but ours, by sheer statistical luck, began in a rare low-entropy state, one that allowed time to flow, stars to form, and life to emerge. Another line of thought involves the idea of gravitational entropy. While matter and radiation were uniformly distributed in the early universe, gravity was waiting in the wings. Unlike other forms of entropy, gravitational entropy increases as matter clumps together. So even though the early universe was uniform, it was actually in a low gravitational entropy state, a condition ripe for structure formation. As gravity took over, it began pulling matter into stars, galaxies, and black holes, increasing the total entropy of the system. This theory offers a partial explanation for why the early universe could be low in entropy overall, while still leading to the complex cosmos we see today. Black holes are the ultimate expression of gravitational entropy. When matter collapses into a black hole, it reaches a state of maximal entropy, so much so that black holes have become central to discussions of thermodynamics and information theory. According to the famous Bekenstein-Hawking formula, a black hole's entropy is proportional to the surface area of its event horizon, not its volume. This peculiar relationship has profound implications. It suggests that the information content of a region of space might be encoded on its boundary, a concept that has given rise to the holographic principle, one of the most compelling ideas in theoretical physics. The holographic principle proposes that all the information contained within a volume of space can be represented on the surface enclosing that space. In other words, our three-dimensional universe may be a projection of information stored on a two-dimensional boundary. This principle, inspired by black hole thermodynamics and later developed through string theory and quantum gravity research, hints at a radical rethinking of the fabric of reality. If space and time themselves are emergent phenomena, not fundamental, but derived from more basic information theoretic rules, then the arrow of time might be a macroscopic illusion, a byproduct of how we experience entropy and information flow. This perspective aligns with a growing body of thought suggesting that time may not be a fundamental entity. In some interpretations of quantum gravity, time emerges from entanglement patterns or from the correlations between quantum states. From this viewpoint, what we perceive as time's flow could be a cognitive construct, shaped by our brain's need to organize sensory inputs into a coherent sequence. Our experience of the now, the present moment, may be no more objective than the redness of an apple or the bitterness of coffee. It's real to us, but it may not exist outside our perception. Yet, even if time is emergent, entropy remains. The second law of thermodynamics holds in every observable context. And because entropy increases, we remember the past but not the future. Memory is an entropic phenomenon. Recording information, whether on a hard drive, a sheet of paper, or the synapses of a brain, requires energy and creates disorder elsewhere. This is why our memories always point backward in time. The process of remembering, like all physical processes, increases entropy. Forgetting, likewise, is a form of entropy, the loss of ordered information back into the chaos of thermal noise. The connection between memory and entropy offers yet another reason for the arrow of time's psychological grip on us. We don't just move through time, we carry the imprint of where we've been. Our identities, our histories, our relationships, all are encoded in memory, and memory only functions in one temporal direction. This asymmetry defines not only the universe's evolution, but also our own. We are entropic beings, born in a flash of low-entropy complexity, and slowly dissolving back into disorder. Yet, in that brief window between order and chaos, we build. We create. We learn. We strive to understand the arrow of time not just as an abstract concept, but as something deeply embedded in our nature. Time pushes us forward, but our awareness of it also pulls us to seek meaning, patterns, and explanations. This perspective forces us to think differently about the nature of time itself. If time's arrow is a byproduct of entropy, then time as we experience it is not a fundamental feature of reality but an emergent phenomenon. It's not that the universe flows from past to future in some cosmic river. Rather, it's that we perceive it flowing because we exist in a system where entropy increases. Our memories, our sense of cause and effect, even the structure of our thoughts, all are built upon this increase. Our brains are thermodynamic machines. Every memory we store, every thought we form, and every action we take is encoded by physical processes that increase entropy. We remember the past because the physical traces of past events exist in a lower entropy configuration that our brains can record. The future, by contrast, has not left such traces, which is why we cannot remember it. This asymmetry is a product of entropy, the very foundation of the arrow of time in human experience. Yet this raises an unsettling question. If the direction of time is tied to entropy, and entropy is ultimately about probability, then could there be regions of the universe, or other universes entirely, where entropy decreases and time runs backward? According to the equations of physics, nothing prohibits such places from existing. In fact, some cosmological models suggest that the universe could be cyclical, with entropy increasing to a maximum, and then somehow resetting or reversing in a new epoch. But this would require an explanation for how entropy could decrease without violating the second law of thermodynamics, which is one of the most well-tested principles in all of science. This law holds so universally because it's statistical. It doesn't say entropy must increase in every tiny system at every moment, only that it almost always does in large systems over time. So while a drop in entropy isn't technically impossible, it is so improbable that we don't expect to see it happen anywhere in our observable universe. Still, some physicists have entertained thought experiments and theoretical models where entropy could, under extreme conditions, decrease in isolated pockets, perhaps during the collapse of a black hole or near the end of time itself. These ideas remain speculative, but they challenge us to reconsider our assumptions about what time really is and how closely it's tethered to thermodynamic principles. And that brings us to one of the most fascinating implications of this entire discussion, the heat death of the universe. If entropy must always increase, and if it drives the arrow of time forward, then the universe is heading toward a state where no more useful energy exists, a state of maximum entropy. This hypothetical end scenario envisions a universe in which all stars have burned out, all matter has decayed, and the only thing that remains is a thin, cold fog of particles drifting through an utterly dark cosmos. In this final state, time would effectively lose meaning. With no processes occurring, no gradients, no motion, no memory, the arrow of time would disappear. The universe would not be dead in the dramatic sense, but it would be completely inert. No life, no activity, no entropy gradients to exploit. Just equilibrium stretching on forever. This stark end is not only a thermodynamic prediction but also a philosophical one. It suggests that time is not eternal. It has a beginning, it has a direction, and it may ultimately come to a stop. But this raises an even deeper question: was there a time before time? Did entropy exist before the Big Bang, or is entropy itself a product of the universe's birth? If we take the second law seriously, then the Big Bang represents not just the origin of space and time, but also the origin of entropy. Prior to that singularity, if such a before even exists, the concept of entropy may have been meaningless. This is one of the reasons why the low entropy starting point of our universe is so mysterious. It seems to require a highly improbable initial condition, and we still have no fully satisfying explanation for it. Various proposals have tried to tackle this. One idea is the past hypothesis, which simply states that the universe began in a low entropy state as a fundamental boundary condition. It doesn't attempt to explain why, it just posits that this is the way it is, and that all the time asymmetry we observe flows from that. Another theory, known as the conformal cyclic cosmology model proposed by Roger Penrose, suggests that the universe goes through infinite cycles of expansion and death, with each cycle beginning in a low entropy state due to the ultimate smoothing out of all structure in the prior cycle. There are also quantum mechanical perspectives to consider. In quantum cosmology, the universe's wave function might contain all possible configurations, including both high and low entropy states. In such models, our universe is one realization of many possible histories, and we happen to exist in the one where entropy started low and increased, because only in such a universe could observers like us arise. This ties closely to the entropic principle, which argues that the universe must be compatible with the conscious beings that observe it, and therefore any explanation of entropy must account for our own existence as part of the picture. From here, the conversation expands into the deep relationship between entropy, consciousness, and causality. We are creatures of memory and anticipation, creatures whose inner lives reflect the asymmetry of time. We remember the past, not the future. We act toward future goals, not past ones. This psychological arrow of time mirrors the thermodynamic arrow, and they are almost certainly connected at a fundamental level. The second law's power lies not in its rigidity but in its reliability as a trend. While small systems can experience temporary drops in entropy due to fluctuations, the larger the system, the more likely it is that entropy will increase overall. This is the fundamental reason why entropy defines the arrow of time, because in a large system, these fluctuations are insignificant and entropy will almost certainly increase. The entire universe, with its staggering complexity and vastness, is a prime example of this principle in action. It reinforces the view that time flows in one direction, from low entropy to high entropy. As we explore the connection between entropy and time, we begin to see that our perception of time's flow is inseparable from the increasing disorder that entropy represents. This link between entropy and time isn't just a physical observation, it shapes the very way we live our lives. From the moment we wake up in the morning, our experience of time is influenced by the ever-increasing entropy of the universe. Our bodies, like everything else in the cosmos, are part of this thermodynamic process, constantly consuming energy, creating order within ourselves at the cost of increasing entropy in our surroundings. This dance between order and disorder mirrors the very flow of time, with each action and event in the universe pushing the arrow of time ever forward. But if we go further, we begin to realize that there is a paradoxical aspect to this. Time, as we experience it, is defined by the progression of events from a past that is locked in memory to a future that is full of possibility. Yet, at the most fundamental levels of physics, time can appear to be reversible. For example, the equations that govern fundamental interactions at the subatomic scale, such as quantum mechanics and the behavior of elementary particles, are often time-symmetric. This means that, in theory, the fundamental laws governing particle interactions would work just as well if time were to flow backward. This seeming contradiction, the everyday experience of time flowing in one direction versus the mathematical symmetry of time at the quantum level, leads to some profound philosophical and scientific questions. How does our perception of time's direction emerge from these underlying laws? Why does time appear to have a flow, when on the fundamental level, it could seem to be reversible? Some physicists argue that the emergence of time's arrow is due to the statistical behavior of systems with large numbers of particles. While the laws governing individual particles might be symmetric in time, the collective behavior of many particles leads to the increase of entropy over time, and thus gives rise to the asymmetry of time that we observe. The more particles involved in a system, the less likely it is that entropy will decrease, and the more certain it is that the future will be more disordered than the past. This process occurs on a scale far beyond what we can directly observe, but it underpins the experience of time that we have in our everyday lives. Now, when we step back and consider the larger cosmic picture, we begin to see that the arrow of time and entropy are deeply interwoven with the very fabric of the universe. From the moment of the Big Bang, the universe has been expanding and evolving, with entropy steadily increasing as structures like galaxies, stars, and planets formed. Over the course of this cosmic evolution, stars have burned through their nuclear fuel, releasing energy into their surroundings and increasing the disorder of the universe. As stars die and scatter their contents across space, entropy continues its steady march forward, setting the stage for the eventual fate of the universe. But what is that fate? If entropy continues to increase, will the universe eventually reach a state where no more work can be done, where all energy is uniformly spread out and no differences in temperature or pressure remain? This scenario is known as the heat death of the universe. In this state, the universe will be a cold, dark, and lifeless expanse. All stars will have burned out, black holes will have evaporated, and all matter will have decayed into subatomic particles. The thermodynamic arrow of time, which has driven the universe from a hot, dense state to an ever-increasing state of disorder, will reach its ultimate conclusion. In the heat death scenario, the flow of time itself would become meaningless. With no processes occurring, no movement, no change, no energy exchange, the concept of time would lose its relevance. Without any events or systems to mark the passage of time, the universe would become a timeless, frozen expanse. This is not just a scientific prediction, but a vision of the universe's ultimate fate that forces us to confront the transient nature of existence itself. Yet, even as we face this stark and seemingly inevitable outcome, there are still mysteries to be explored. The idea of entropy and the arrow of time ties directly into questions about the ultimate origins of the universe. The low entropy state at the beginning of the universe, as outlined by the second law of thermodynamics, remains one of the most profound and unexplained aspects of modern cosmology. How did the universe begin with such a low entropy state, and why did it evolve in such a way that entropy would increase? Some cosmological models propose that our universe might be part of a larger multiverse, a collection of universes with different properties, some of which might experience a different flow of time, or even different laws of thermodynamics. In such a scenario, the laws of entropy could vary between universes, leading to different experiences of time and disorder. Others suggest that the low entropy state at the beginning of our universe may have been a necessary condition for the existence of life and the structures that support it. Whatever the answer, the connection between entropy, time, and the universe's origins remains one of the most profound and elusive mysteries in science. As we continue to explore these ideas, we must also grapple with the deep philosophical questions they raise. What is time really? Is it an inherent feature of the universe? Or is it something that arises from the way we experience the world around us? If time is tied to entropy, what does this mean for the possibility of time travel or the nature of the future? And ultimately, what does the eventual heat death of the universe say about the ultimate fate of everything, including ourselves? As we dive deeper into the philosophical and scientific implications of entropy and the arrow of time, we come face to face with some of the most perplexing and profound questions that challenge our understanding of reality itself. What is time, and how does it relate to our experience of the universe? If entropy governs the flow of time, is there any possibility of reversing it, or are we forever bound to watch as the universe steadily progresses toward disorder and decay? These are questions that have fascinated not only scientists but also philosophers, who have long pondered the true nature of time. One of the central ideas that has emerged from both physics and philosophy is that time, as we perceive it, may not be an inherent feature of the universe but rather a product of our own perception. Our experience of time as a continuous flow, from past to present to future, could be the result of the way our minds process events and changes in the world around us. In other words, time may not be something that exists independently of us but something that arises from the patterns of change we observe. This idea is challenging because it forces us to reconsider not only our understanding of time but also our place in the cosmos. Moreover, if time is indeed a product of perception, this leads to questions about the nature of our experience. If time is merely a framework for understanding change, does it have any absolute meaning beyond our minds? And if the passage of time is tied to the increase of entropy, does this mean that our perception of time itself is intimately connected to the thermodynamic properties of the universe? These philosophical questions bring us back to the concept of the heat death of the universe. If the universe eventually reaches a state where all energy is evenly distributed, and all processes cease, then time, as we know it, would lose all significance. There would be no events, no changes, and no way to measure the passage of time. In this sense, the heat death represents not just the end of the universe but the end of time itself. The finality of this scenario raises deep existential questions about the nature of existence, the role of time in our lives, and the ultimate fate of everything we know. Despite the seemingly inevitable nature of entropy's progression, however, there are still many mysteries surrounding the arrow of time and its relationship to the universe. One of the most intriguing questions is whether time travel could ever be possible. If time flows in one direction, from past to future, can we ever travel backward in time or alter the course of events? This question has been the subject of much speculation in both science fiction and theoretical physics. Some theories suggest that time travel might be possible under certain conditions, such as through the manipulation of spacetime using wormholes or by traveling at speeds close to the speed of light. While these ideas remain speculative, they point to the possibility that our understanding of time is far from complete. Just as the concept of time itself might be more flexible than we once thought, the connection between time and entropy may hold more mysteries than we can currently comprehend. If time travel were to become possible, it would challenge our very understanding of causality and the arrow of time. It would force us to reconsider the relationship between entropy, the flow of time, and the nature of events in the universe. At the same time, the idea of time travel also raises the possibility of reversing entropy. If time travel were possible, could it allow us to undo the effects of entropy and restore order to a system that has become disordered? While this may seem like a tantalizing prospect, it would require a fundamental shift in our understanding of the second law of thermodynamics. To reverse entropy on a large scale, we would need to find a way to create localized decreases in entropy without violating the overall trend of increasing disorder. This would involve enormous amounts of energy, and may not be feasible within the constraints of current scientific knowledge. Yet, the very fact that these questions are being asked suggests that our understanding of the arrow of time and entropy is still incomplete. The mysteries of time, entropy, and the universe are far from solved, and as our scientific understanding advances, we may find that the flow of time is more flexible than we ever imagined. We may discover new ways to manipulate entropy, or even unlock secrets that allow us to reverse its effects on a small scale. As we continue to explore these mysteries, it's important to remember that the study of entropy and time is not just a theoretical exercise. The principles of thermodynamics and the arrow of time have real-world applications in fields ranging from cosmology to information theory to engineering. The concept of entropy has been instrumental in developing technologies such as engines, refrigerators, and even the very computers we use to process information. In information theory, entropy is used to measure the amount of uncertainty in a system, helping engineers and computer scientists design more efficient communication systems. In the context of the universe, entropy also plays a key role in the formation of stars, galaxies, and other cosmic structures. The evolution of the cosmos is shaped by the interplay between gravity, radiation, and entropy, and understanding how these forces work together can help us unlock the secrets of the universe's past, present, and future. As we learn more about entropy and time, we are not just gaining insight into abstract concepts, we are uncovering the fundamental processes that govern the universe itself. But perhaps the most profound takeaway from the study of entropy and time is the realization that time is not just something we experience, but something that is woven into the very fabric of reality. The progression of time, from past to present to future, is inseparable from the increase of entropy, a process that shapes not only the cosmos but also our lives. Every moment, every action, every change we experience is a manifestation of the passage of time and the relentless march of entropy. As we face the eventual heat death of the universe, we are reminded of the impermanence of all things. The universe will continue to evolve, and entropy will continue to increase, until all that remains is a state of maximum disorder. But in the meantime, we have the opportunity to experience the flow of time, to witness the unfolding of events, and to contribute to the patterns of order and disorder that define our existence. In this way, the study of entropy and the arrow of time is not just an exploration of cosmic forces, but an invitation to reflect on our own place in the universe and the fleeting nature of our experience. The ultimate fate of the universe, bound by the inexorable laws of entropy, may seem bleak, but it also offers us a profound perspective on the preciousness of life, time, and existence. The more we understand about the nature of time and entropy, the more we are reminded that every moment counts, that every event and every action we take is a part of the ongoing story of the universe. Time, in its passage, carries us forward, and it is up to us to make the most of the time we have. As we continue to explore the relationship between entropy and the arrow of time, it becomes clear that our understanding of time is not just a scientific matter, but also a deeply philosophical one. The more we learn about how the universe unfolds, the more questions arise about the nature of existence and our place within it. Time is a mysterious force that shapes our lives, yet it remains elusive, slipping through our fingers like grains of sand. How do we reconcile the seeming inevitability of entropy, which drives everything towards disorder, with our desire for meaning, order, and purpose? To consider this more deeply, let's take a step back and think about the role of entropy on a more personal level. Every day, we experience small increases in entropy, our coffee cooling down, our rooms getting messy, or our bodies aging. These are all examples of how entropy manifests in our immediate surroundings. But what if we shift our perspective and think about entropy not just in terms of physical objects, but as a reflection of the larger forces at play in the universe? In many ways, entropy is a reminder of the transient nature of everything around us. It teaches us that all systems, no matter how ordered they seem, will eventually reach a state of equilibrium, where no further work can be done. This is not just true for the universe as a whole but for our own lives. Our actions, our experiences, and even our memories, all are subject to the influence of entropy. This can be both a humbling and a liberating realization. In one sense, the inevitability of entropy highlights the fragility of life and the universe, but in another, it also encourages us to live fully in the present moment, knowing that time is fleeting. If we look at entropy through a more practical lens, we can see that it provides a framework for understanding the direction of physical processes. In thermodynamics, the second law states that entropy must always increase in a closed system. This law governs everything from the functioning of engines to the behavior of gases and fluids. Yet, this seemingly simple rule carries profound implications for our understanding of the universe. Consider the process of cooling, for instance. When a hot object is placed in contact with a cooler one, heat flows from the hotter object to the cooler one until both objects reach thermal equilibrium. This process is governed by the second law of thermodynamics. As it represents an increase in entropy, the heat energy becomes more evenly spread out. The concept of entropy in this case is not just about disorder, but about the dispersal of energy. In a sense, energy always seeks to spread out and become more evenly distributed. This is why, in the grand scale of the universe, the ultimate fate of everything is to reach a state of maximum entropy, a state of thermal equilibrium. The idea of thermal equilibrium is not just an abstract concept. It has real-world applications that help shape the technologies we use every day. Take engines, for example. In an engine, fuel is burned to produce heat, which is then used to do work. The engine operates by taking advantage of the difference in temperature between the hot and cold parts of the system, allowing heat to flow from the hot side to the cold side, doing work in the process. This process, known as the heat engine cycle, is based on the principles of thermodynamics, including the idea of entropy. The more efficiently we can harness and control the flow of energy, the more we can do with the energy available to us. At the cosmic scale, entropy also plays a central role in the formation and evolution of the universe. The process of stellar formation, for example, involves the collapse of gas clouds under gravity, which heats up the gas and causes nuclear fusion to begin. This release of energy from stars represents a local decrease in entropy, as energy is concentrated in a specific area. However, the overall entropy of the universe increases as energy is radiated away from the star, contributing to the overall trend of increasing disorder. The birth and death of stars are part of the larger cycle of entropy in the universe, and each star's life is a brief but significant chapter in this ongoing story. Similarly, galaxies themselves are constantly evolving, as they undergo cycles of star formation, supernova explosions, and the eventual death of stars. In these processes, the distribution of energy and matter changes, contributing to the overall increase in entropy. Even the formation of black holes, one of the most mysterious and powerful phenomena in the universe, is governed by the principles of entropy. When matter is compressed to the point of forming a black hole, it represents an extreme increase in entropy, as all the energy and information within that region becomes trapped inside the event horizon. While entropy governs the evolution of the universe, it also opens up new avenues of inquiry. One of the most exciting and perplexing questions in modern physics is whether entropy can be bent or manipulated in ways that might allow us to control or reverse its effects. This idea brings us back to the topic of time travel and the potential to change the course of events. Could we, in theory, reverse the flow of time and decrease entropy in certain systems? Some physicists have suggested that time travel could, in theory, allow us to undo the effects of entropy, but this remains highly speculative. Nonetheless, the possibility that time itself could be manipulated in ways we don't yet understand hints at the vast potential for discovery in the realm of physics. As we explore these ideas, it's important to remember that the nature of time, entropy, and the universe is still largely unknown. We have only scratched the surface of these profound questions. Theories like string theory and quantum mechanics offer glimpses into new dimensions of reality, but the full picture remains elusive. Perhaps, in the future, we will find ways to understand and even manipulate time and entropy in ways that are unimaginable today. This exploration of time and entropy is not just about theoretical physics or abstract concepts, it touches on some of the deepest questions about life and existence. Our understanding of time shapes how we live, how we perceive our own experiences, and how we relate to the universe around us. Time is both a practical and a philosophical issue, something that governs our daily lives while also being a source of profound mystery. We are left with more questions than answers. What does it mean to live in a universe governed by entropy? How can we reconcile our experience of time with the scientific understanding of its nature? These questions are not easy to answer, and they may not have answers at all. But one thing is certain, the study of entropy and time has the power to transform our understanding of the universe and our place within it. In the end, the arrow of time and the increase of entropy may be our greatest teachers, reminding us that time is precious, that change is inevitable, and that the universe is forever in flux. As we continue our deep dive into the mysteries of entropy and time, the very act of contemplating these concepts allows us to grapple with our own existence in a more profound way. Entropy, the inevitable tide that pulls everything toward disorder, might seem like a harsh, unavoidable force. But in another sense, it can also serve as a subtle reminder of how precious and finite life truly is. After all, if everything eventually breaks down, if systems and structures are destined to become more disordered over time, then each moment of clarity, each instance of order, becomes that much more meaningful. This realization touches on something even more profound than scientific inquiry, the way we, as conscious beings, experience the flow of time and the changes that occur around us. We perceive the passing of time, and we observe the gradual erosion of order into chaos in our own lives. From aging bodies to decaying objects, the evidence of entropy is undeniable. But in our daily experiences, time seems to flow in only one direction, forward, from one moment to the next. The past is gone, and the future is always just out of reach, slipping away as we approach it. This sense of the arrow of time is something that we all feel intimately. Yet understanding why time flows only in one direction is one of the greatest puzzles of modern physics. The second law of thermodynamics, which dictates that entropy must increase in a closed system, gives us some insight into this directional flow. As entropy rises, systems evolve from order to disorder, and this progression mirrors the passage of time. But why, exactly, does time flow in this particular direction? One hypothesis that addresses this question comes from the field of cosmology. The Big Bang, which marks the birth of our universe, is believed to have been an event of extremely low entropy. In the moments immediately following the Big Bang, the universe was in a highly ordered state. As it expanded and cooled, entropy began to increase, and the universe became more complex. Stars, galaxies, and planets formed, and the process of thermodynamic evolution began. From this perspective, the arrow of time is tied to the increasing entropy that began with the Big Bang and has continued to unfold ever since. This connection between the Big Bang and the arrow of time offers a fascinating lens through which we can view the universe. It suggests that time itself is inherently tied to the growth of disorder. The very fact that we experience time as flowing forward, that we age, that objects break down, that the universe is constantly evolving, can be seen as a consequence of this universal law. As entropy increases, so does the passage of time. However, there are still many unanswered questions about the relationship between entropy and time. For example, how does the direction of time relate to our subjective experience? While we may observe time flowing in one direction, we still don't have a complete understanding of how our perception of time arises in the brain. Is time something we experience because of the way our brains process events? Or is it something more fundamental, a property of the universe itself that we are simply tuned to observe? This brings us back to the philosophical implications of entropy and the arrow of time. If everything in the universe is destined to eventually reach a state of maximum entropy, does that mean our lives, too, are destined to fade into oblivion? The idea of a universe ultimately heading towards heat death, a state where no usable energy remains and no processes can occur, is a sobering thought. But it also raises profound existential questions. Does the increasing entropy of the universe render life meaningless, or does it give meaning to the moments we experience, precisely because they are fleeting? One fascinating aspect of entropy is that, despite its tendency to drive everything toward disorder, local decreases in entropy are possible. For example, living organisms represent a temporary decrease in entropy. A living organism, like a tree, an animal, or a human, maintains a state of relative order for a time, using energy to build and maintain complex structures. This ability to decrease entropy locally, to create and sustain life, is what allows us to experience consciousness, creativity, and growth. But eventually, all living things succumb to the forces of entropy, as they age, decay, and break down. This balance between the temporary decreases in entropy within living systems and the overarching increase in entropy throughout the universe is what makes life so fascinating. It is an ongoing dance between order and chaos, creation and destruction, that mirrors the grand story of the cosmos. Just as a tree grows, flowers bloom, and animals evolve, all of these processes are part of the ever-expanding movement toward a state of greater entropy. In this sense, the universe itself can be seen as a vast, interconnected system of entropy, constantly changing and evolving. But how does this all relate to the human experience? We can look at entropy as a metaphor for the challenges and changes we face throughout our lives. Like the universe, we too experience an inevitable progression from order to disorder, from youth to old age, from health to illness. The physical bodies we inhabit are subject to entropy in the same way that galaxies, stars, and planets are. This is a powerful reminder that our lives, too, are part of a larger cosmic narrative, one that is ultimately beyond our control. Yet, even as we are bound by the laws of entropy, we also have the ability to influence the course of our lives in ways that make a difference, if only temporarily. In our pursuit of knowledge, in our creativity, and in the connections we form with others, we push against the tide of entropy, at least for a while. The fleeting moments of beauty, of love, of innovation, these are our victories against the encroaching disorder. In the grand scheme of things, these moments may be brief, but they are deeply meaningful nonetheless. The very fact that we can create, experience, and appreciate order in the midst of chaos is what gives our lives depth and significance. And so, the relationship between entropy and time is not just an intellectual pursuit, but also a deeply human one. It compels us to reflect on our existence, our purpose, and the role we play in the universe's unfolding narrative. Are we mere passengers on a train speeding toward the eventual heat death of the cosmos? Or are we creators, actively shaping the course of time in ways that leave a lasting impact? The arrow of time and the ever-increasing entropy of the universe remind us that time is a precious, limited resource. Every moment we experience is a temporary victory over the forces that seek to unravel all order. It's a reminder to live with purpose, to make the most of our fleeting existence, and to cherish the beauty of a universe that, despite its inevitable drift toward disorder, continues to offer us moments of wonder, discovery, and joy. The Big Bang is believed to have marked the moment when entropy was at its absolute minimum, a state of almost perfect order. From that origin point, the universe expanded rapidly, distributing matter and energy throughout space and triggering a gradual but relentless increase in entropy. In this perspective, the arrow of time emerged hand in hand with the universe itself. Time flows forward because entropy has been increasing ever since that cosmic birth. This idea helps explain why we experience time as moving in one direction and not the other. It's not that the fundamental laws of physics prevent time from going backward. In fact, many of them are time-symmetric, meaning they don't prefer one direction of time over another. But the second law of thermodynamics does impose a preferred direction: entropy must rise. So even though the microscopic laws allow for time to run backward, the macroscopic trend toward disorder creates a global asymmetry, a distinction between past and future. This asymmetry is reflected in everything from the shattering of glass to the mixing of cream into coffee. We never see a shattered glass reassemble itself, or cream unmixed from coffee, because such processes would involve a decrease in entropy, which is statistically improbable. The second law doesn't make these events impossible, just so extraordinarily unlikely that they effectively never happen. And this statistical nature of the second law is crucial to understanding why entropy rises at all. Entropy is not a force or a substance, it's a measure of the number of ways a system can be arranged. When a system has low entropy, there are only a few ways its components can be organized. But as entropy increases, the number of possible configurations rises dramatically. The most probable states are the ones with the highest number of configurations, the most disorder, and so systems naturally evolve toward them. This evolution is what drives the irreversible processes we see all around us. Ice melts, stars burn out, and living organisms age. All these changes are guided by the statistical pull toward more disordered states. Even memory, one of the key features of our conscious experience, may be tied to this flow. We remember the past because it was a state of lower entropy, where records and traces were more clearly defined. The future, by contrast, hasn't happened yet and hasn't left any entropy-laden traces. This gives rise to our psychological arrow of time, the subjective feeling that time flows in one direction. What's even more fascinating is that this thermodynamic arrow of time may not be the only one. In addition to the psychological arrow, there are others: the cosmological arrow, marked by the expansion of the universe, the electromagnetic arrow, pointing in the direction of light's radiation, and the quantum arrow, related to wave function collapse in quantum mechanics. Each of these arrows generally aligns with the thermodynamic one, but whether this alignment is a coincidence or a deeper law of nature is still unknown. Time, entropy, and causality are intertwined in ways we're only beginning to understand. The increase of entropy doesn't just give direction to time, it might also define what it means for something to cause something else. In a low-entropy past, we can point to specific causes and trace chains of events forward. But as entropy increases, these chains become tangled, outcomes become more probabilistic, and predictability fades. Cause and effect rely on order and structure, both of which entropy relentlessly erodes. And yet, within this forward march of entropy, life manages to carve out small, temporary pockets of order. Living systems, including humans, are remarkable in their ability to maintain low internal entropy while increasing the entropy of their environment. We take in energy in ordered forms, like food or sunlight, and release it in disordered forms, like heat. In doing so, we sustain ourselves and create islands of order in a sea of chaos, albeit temporarily. This thermodynamic balancing act is at the heart of biology, evolution, and even consciousness. When we say that systems evolve toward higher entropy, what we're really saying is that they evolve toward states that are statistically more likely. Consider a deck of cards as a simple metaphor. A perfectly ordered deck, with all suits and numbers in sequence, represents a low-entropy state. There are very few arrangements that constitute this exact order. But shuffle the deck, and the likelihood of returning it to that ordered state is astronomically low. There are billions of possible configurations, and only one is perfectly ordered. Thus, the disordered states vastly outnumber the ordered ones, and the entropy increases with each shuffle. This principle applies not just to card games but to stars, galaxies, molecules, and everything else in our universe. Entropy also provides a key to understanding why memories work the way they do. We remember the past, not the future. Why is that? One explanation lies in the trail of information left behind by increasing entropy. Events in the past create records, physical imprints in our brains, in photographs, in fossilized footprints, that we interpret as memories. These records are only possible because of the progression from low to high entropy. The future hasn't happened yet, so it hasn't left any records. That's why we have no memory of it. In this way, entropy shapes not only the physical world but also the way we perceive and experience time. As entropy increases, complexity doesn't necessarily vanish. In fact, within this overall trend toward disorder, islands of complexity can temporarily form. Life itself is one of these islands. The Earth receives energy from the Sun, which allows it to support life and maintain complex systems. But even as local entropy decreases within a living organism, such as when cells form or when a plant grows, the total entropy of the system, including the surroundings, still increases. Life builds order at a local scale while contributing to disorder on a universal scale. This dynamic is fascinating because it suggests that complexity and structure are not incompatible with entropy. Rather, they exist within it. The emergence of galaxies, stars, planets, and even intelligent life can be seen as part of entropy's grand narrative. These systems form in ways that ultimately maximize entropy over time. It's not that order violates the second law of thermodynamics, but that order arises in service of it, temporary structures that help accelerate the breakdown of energy gradients. Zooming out to the scale of the cosmos, we find that entropy will one day reach a maximum. This is known as the heat death of the universe, a theoretical state in which all energy is evenly distributed, and no more work can be done. Stars will burn out, black holes will evaporate, and all matter will reach thermal equilibrium. In this state of maximum entropy, time may lose its meaning, because without change or differentiation, there's nothing by which to measure its passage. The arrow of time, so prominent in our current epoch, might cease to function in any practical sense. But before that ultimate fate, we are living in an age of relative entropy imbalance. The universe is still far from equilibrium, and energy differences abound. These differences are what drive everything from the fusion in stars to the functioning of your brain. In fact, your thoughts, right now, as you read this, are powered by entropy gradients. The glucose in your body is broken down in reactions that increase entropy, releasing energy that fuels neurons and maintains your conscious awareness. Even time itself might be a product of entropy gradients. Some theories suggest that time is not a fundamental entity, but an emergent one, a byproduct of entropic processes. In these models, time arises from the relationship between different parts of a system, each experiencing its own local increases in entropy. This would mean that time isn't something that exists independently, like a river flowing from past to future, but something that bubbles up from the thermodynamic behavior of the universe. This possibility turns many of our assumptions upside down. If time is emergent, then so are causality, history, and maybe even the self. What does it mean to be you, if your sense of identity is built on a temporal foundation that isn't fundamental? Perhaps consciousness, too, is a thermodynamic phenomenon, a temporary fluctuation in entropy that allows a self-aware structure to arise and reflect upon its own impermanence. There's also a fascinating intersection between entropy and information theory. In this field, pioneered by Claude Shannon, information is measured in a way that mirrors entropy. The more uncertainty there is in a message, the more information it contains. This is why randomness is considered highly informative. Paradoxically, this connects the concepts of disorder and information. The higher the entropy, the more unpredictable the system, and the more data it holds. This relationship is not just mathematical, it underpins our understanding of everything from data compression to black hole physics. Speaking of black holes, they offer one of the most extreme laboratories for studying entropy. According to physicists Jacob Bekenstein and later Stephen Hawking, black holes possess entropy proportional to the area of their event horizon. This discovery revealed something shocking. Black holes are not entirely black. They emit radiation, now known as Hawking radiation, and over incredibly long timescales, they can evaporate. This means they lose mass and energy, and their entropy decreases. But this process is so slow that it takes longer than the current age of the universe for a black hole to evaporate completely. However, black holes also pose one of the deepest mysteries in physics, the information paradox. When matter falls into a black hole, what happens to the information it carries? Quantum mechanics insists that information cannot be destroyed, but classical black hole theory suggests it is lost forever. Resolving this contradiction is a major goal in the quest for a unified theory of quantum gravity. Some proposed answers involve holographic principles, where all the information swallowed by a black hole is somehow encoded on its surface, like a cosmic hard drive. If this idea is true, it could imply that the entire universe is, in some sense, a hologram, a three-dimensional reality encoded on a two-dimensional boundary. This concept, while speculative, has real mathematical support and deep implications for the nature of space, time, and entropy. It challenges our assumptions about where information resides and how entropy evolves in the context of quantum gravity. Entropy is not just a thermodynamic principle. It's a key that unlocks some of the deepest questions in physics, consciousness, and cosmology. It drives stars and civilizations alike. It shapes time, carves memory, and governs the birth and death of galaxies. To understand entropy is to glimpse the architecture of the universe, not as a fixed, eternal structure, but as a restless, ever-unfolding process of transformation. This delicate balancing act highlights a fundamental truth about how complex systems like life operate within an entropic universe. Living organisms build and maintain order internally, but only by tapping into energy sources that ultimately contribute to a greater increase in entropy elsewhere. The food we eat, the sunlight we absorb, the oxygen we breathe, all of these are inputs that allow us to resist internal chaos temporarily. But in the grand ledger of entropy, we're always paying a higher cost to the universe around us. Even the emergence of consciousness, one of the greatest mysteries in science, might be seen through the lens of entropy. Our brains are intricate networks, constantly receiving, processing, and responding to information. They generate heat, consume vast amounts of energy, and maintain a level of internal structure that defies the general trend of disorder, for a time. But this activity contributes to the overall entropy of the environment. The brain may be one of the most ordered systems we know, but it is not immune to decay. Over time, neurons misfire, pathways degrade, and memory fades. Entropy finds its way, even here. The arrow of time also plays a role in how we experience emotions, growth, and aging. We feel nostalgia because the past is fixed. It's a reference point in a sea of ever-increasing uncertainty. Our future, by contrast, is always indeterminate. As entropy increases, so does the unpredictability of complex systems. This is why we can plan for the future, but we can't guarantee it. The more complex a system becomes, the more susceptible it is to small changes that can drastically alter outcomes, a phenomenon closely tied to chaos theory. Chaos, interestingly, is not the same as entropy, though they're often confused. Entropy is about the number of possible states a system can occupy, its disorder. Chaos, on the other hand, refers to sensitivity to initial conditions in a deterministic system. A chaotic system follows predictable rules, but small differences in starting conditions can lead to wildly different results. Weather is a classic example. It's governed by physical laws, but long-term forecasting is nearly impossible because of this sensitivity. The connection between chaos and entropy lies in their shared unpredictability. As entropy increases, systems become more chaotic, less orderly, and harder to reverse. Let's now look at black holes, the cosmic titans where entropy reaches its zenith. According to physicist Jacob Bekenstein and later confirmed by Stephen Hawking, black holes have entropy, and not just a little, but a staggering amount. This discovery reshaped our understanding of entropy and thermodynamics. The surface area of a black hole's event horizon, not its volume, is proportional to its entropy. That's mind-bending, a three-dimensional object's disorder being measured by a two-dimensional boundary. It hints at a deeper truth about the nature of the universe, one that suggests the fabric of reality may be encoded on its surface, an idea that would eventually evolve into the holographic principle. Black holes also raise another thorny issue, the information paradox. When matter falls into a black hole, where does the information about its quantum state go? According to quantum mechanics, information can't be destroyed. But black holes seem to violate this principle. As they evaporate via Hawking radiation, they appear to erase all information about what fell in, a violation of quantum theory and the second law of thermodynamics if entropy is lost in the process. This paradox has inspired some of the most cutting-edge theories in physics today, from string theory to quantum gravity, all attempting to reconcile these two pillars of modern science. Another profound implication of entropy lies in the concept of heat death, the hypothetical end state of the universe. As entropy increases, usable energy becomes increasingly scarce. Stars burn out, galaxies drift apart, and black holes slowly evaporate. Eventually, the universe could reach a state of maximum entropy, where no work can be done, no information processed, and no life sustained. This bleak scenario is known as the heat death of the universe. It's a future where time itself loses meaning because no changes are happening, all gradients have flattened out. Yet, even in this grim vision, some physicists see hope or at least curiosity. New theories suggest that fluctuations in the vacuum of space might allow for the spontaneous creation of new low-entropy regions, perhaps even new universes. These fluctuations would be incredibly rare and slow, but in the vastness of eternity, even the improbable becomes inevitable. This idea echoes a kind of cosmic rebirth, that entropy might not be the end, but a transition point to something we can't yet imagine. Meanwhile, in our corner of the cosmos, entropy continues to shape everything. It explains why your coffee cools, why buildings crumble, and why we age. It underlies the ticking of every clock, the burning of every star, and the unfolding of every moment. Entropy is not just a scientific concept, it is a cosmic storyteller, narrating the tale of time through the language of disorder. And this narrative, written into the very structure of our universe, is ongoing. Even as we develop advanced technologies, seek out new frontiers in space, and unlock the mysteries of quantum mechanics, entropy looms as both a challenge and a guide. Understanding it doesn't just deepen our comprehension of physics, it sharpens our awareness of life's fleeting beauty, and the fragile order we create in a universe tending toward chaos. This relationship between chaos and entropy becomes especially important in cosmology. As the universe evolves, it undergoes processes that both display chaotic behavior and contribute to the overall increase in entropy. Stars explode in supernovae, scattering heavy elements across space. Galaxies collide, warping and twisting under gravitational forces. Black holes form, devouring matter and energy. Each of these events adds to the disorder, increasing the entropy of the universe. Yet, in the midst of this cosmic chaos, temporary structures emerge: stars, planets, biospheres, each a brief defiance of the entropic tide. Black holes, in particular, present a fascinating paradox when it comes to entropy. According to physicists Jacob Bekenstein and later Stephen Hawking, black holes have entropy. In fact, they have an immense amount of it. Hawking discovered that the entropy of a black hole is proportional to the surface area of its event horizon, not its volume. This led to the famous concept that black holes radiate energy, what we now call Hawking radiation. Over time, they slowly evaporate, releasing energy back into the universe. And as they do, the information paradox emerges. What happens to the information that fell into the black hole? This puzzle is central to modern theoretical physics. If information is truly lost in a black hole, it would violate the principle of unitarity in quantum mechanics, the idea that information is conserved. But if the information is somehow preserved, perhaps encoded in the Hawking radiation or on the event horizon itself, then our understanding of entropy, time, and the nature of reality may need to evolve. The holographic principle, an idea born from string theory, suggests that all the information contained in a volume of space may actually be encoded on its boundary, much like a hologram. This notion ties back into the entropy of black holes and reshapes how we view the very structure of space-time. The arrow of time is not only found in physics but is deeply embedded in our psychology and biology. From the moment we are born, we begin aging. This process is a march toward disorder. Cells divide, DNA accumulates, damage, systems wear down. While we can slow this progression with lifestyle and technology, we cannot reverse it. Entropy ensures that time flows in one direction, forward. And as we age, our memories accumulate in only one direction. We remember the past, never the future. This asymmetry defines our human experience. What's fascinating is that even though entropy tends to increase, life and intelligence are incredibly adept at finding ways to delay that increase locally. We build machines, cities, civilizations. We organize resources, plan for the future, and create systems of knowledge that persist through generations. But each of these efforts, while creating local order, ultimately contributes to the greater disorder of the universe. A computer processes information efficiently, but it also releases heat. A rocket escapes Earth's gravity, but only by burning fuel and leaving behind spent stages. There is always a cost. In a way, humanity is like a ripple in the fabric of entropy, a burst of ordered complexity that emerged for a brief period in the cosmic timeline. Our technology, our dreams, our art and science, these are acts of temporary rebellion against entropy. But we can never escape its grasp entirely. Even the most sophisticated artificial intelligences we develop, the most powerful quantum computers we imagine, are still bound by thermodynamic principles. They too must obey the law of increasing entropy. The ultimate fate of the universe may well be dictated by this law. One prevailing theory is the heat death of the universe, a future state in which all energy is evenly distributed, and no work can be performed. Stars will burn out, black holes will evaporate, and everything will drift toward thermal equilibrium. No gradients, no order, no complexity. Just a cold, dark cosmos in a state of maximum entropy. Time, in such a universe, may lose all meaning. With no change, no events, no memories, what does before and after even mean? Yet we are not there yet. We live in a moment of extraordinary entropy gradients, a time when stars still burn, life still thrives, and complexity continues to emerge. And in this moment, we can marvel at the arrow of time not just as a law, but as a mystery. Why did the universe begin in such a low entropy state? Why does time move forward at all? These questions remain among the greatest unsolved problems in physics and philosophy. They remind us that for all we know about entropy, we are still humbled by what we don't. From a broader perspective, the universe's evolution toward increasing entropy shapes everything, not just the structure of galaxies and the death of stars, but the conditions for the emergence of life, the passing of history, and the trajectory of civilizations. This universal increase in disorder is not merely a scientific observation but a profound narrative, a silent current carrying every atom, organism, and thought in one direction only. It is the canvas on which all of history is painted, from the birth of the cosmos to the inevitable heat death that awaits in the far future. Entropy's inexorable pull sets the stage for everything, and no matter how much we strive for permanence, the direction is fixed. Buildings will crumble, languages will fade, and even the greatest achievements of intelligence may one day be swallowed by the quiet, cold darkness of an entropic end. Yet this isn't a story of despair. Entropy is not an enemy. It is the backdrop against which complexity arises and meaning is created. Without the asymmetry of time, without the constant movement from order to disorder, there could be no growth, no change, no progress. The arrow of time is not a curse, but the very condition for experience, memory, and evolution. Without it, the universe would be static and lifeless, a frozen tableau with no past and no future. But time flows, and in that flow, there is room for wonder. The stars that burn bright today do so because the universe is still rich with energy gradients. Our existence, brief and improbable as it is, rides on the crest of that gradient, a momentary spike in the sea of increasing entropy. Thermodynamics, in this sense, tells a deeper story about the fragility of order. It teaches us that equilibrium is not a goal, but a grave. Systems left to themselves move toward uniformity, and that uniformity is the cessation of all structure. A cooled universe with no difference in temperature, no chemical gradients, no gravitational anomalies, that is the destiny of unchecked entropy. And yet, within that context, our very resistance to that fate becomes all the more remarkable. Every act of creation, of learning, of communication, is a tiny rebellion against the default trajectory. And every such act comes at a cost. We burn fuel, dissipate energy, and push disorder into the world around us, just to keep our own internal structures intact for a little while longer. This tension between local order and global disorder is what makes life possible. It is what allows stars to shine, planets to spin, and minds to think. And as strange as it sounds, this interplay is encoded in the very molecules of our DNA. Evolution itself is a thermodynamic process, dependent on the flow of energy through organisms and the ability of those organisms to convert, use, and adapt to that energy flow. The survival of the fittest is also the survival of the most thermodynamically efficient. Entropy doesn't just govern the fall of empires, it shapes the wings of birds, the colors of flowers, and the neural pathways that give rise to love and language. The psychological arrow of time, our unshakable sense of past, present, and future, is deeply rooted in this thermodynamic reality. We remember the past because it was more ordered, more constrained. The future, by contrast, is open to infinite possibilities, most of them more disordered than the present. Our memories are records of low-entropy configurations. Once that configuration is disturbed, it cannot be restored, and thus we cannot unremember. This is why we can never truly go back. The future might hold endless wonders, but it will never recapture the precise state of what once was. In light of this, entropy also challenges our notions of permanence. What does it mean to build something that lasts? Every monument we construct, every digital archive we curate, is ultimately engaged in a battle against time's one-way current. The pyramids may stand for thousands of years, but wind and sand will eventually wear them down. Digital data, too, faces degradation, magnetic decay, cosmic radiation, and technological obsolescence. Even the great cultural artifacts, the masterpieces of music and art, rely on fragile media and human memory to endure. Entropy spares nothing, not even our most cherished expressions of meaning. And yet, in our attempts to preserve, to record, and to remember, we create a kind of echo. These echoes ripple forward, influencing future minds, future decisions, future creations. The arrow of time cannot be reversed, but it can be marked. Like footprints in the sand, the things we do leave traces, temporary impressions that others can follow before the tide of disorder washes them away. In this way, the human story becomes a dance with entropy, not a triumph over it, but a continuous negotiation. We may never escape the second law of thermodynamics, but we can use it to understand who we are, why we remember, and what it means to exist in a universe that only moves one way. This ongoing dance between creation and dissolution, between order and chaos, unfolds not only in the physical world but in the conceptual realms as well. Our understanding of time, of memory, and of the future is inexorably shaped by the entropic flow of the universe. For instance, the entropy of our thoughts plays a pivotal role in the way we process and recall information. Cognitive science suggests that the brain, a marvel of complexity, is constantly fighting against disorder to maintain its coherence. Our memories, for instance, are not fixed entities. They are dynamic constructs, constantly reshaped by time and experience. Every time we recall an event, we reconstruct it, adding new details, distorting others, and in the process, increasing its entropy. The original, pristine memory is never fully recovered, and what we remember is but an approximation of what once was. In this sense, the mind is engaged in a continuous battle against entropy, trying to preserve a sense of continuity and identity in a world that is constantly shifting. At the heart of this struggle is the notion of time itself. Time, in its most fundamental sense, is intrinsically tied to entropy. In thermodynamics, time is not a mysterious force that exists on its own. It is the measure of change in a system. And change, in turn, is driven by the flow of entropy. When we experience time passing, what we are really perceiving is the relentless march of disorder creeping through the fabric of existence. This is why we can never replay the past, because the entropy of the moment has already scattered the original configuration beyond our reach. Time, in this view, is a one-way street, carrying us ever forward toward greater randomness and greater disorder. In the realm of cosmology, the arrow of time and entropy work in tandem to dictate the evolution of the universe. The Big Bang, the birth of stars, the formation of galaxies, all of these events can be understood as processes that contribute to the increase in entropy. Initially, the universe began in a highly ordered state, with the energy concentrated in a hot, dense singularity. Over time, as the universe expanded and cooled, this energy dispersed, forming matter and radiation, galaxies, and eventually stars. The process of stellar fusion, for instance, is a direct consequence of increasing entropy. Stars burn through fuel, releasing energy and producing heavier elements, but in doing so, they also increase the overall entropy of the universe. When a star reaches the end of its life and explodes in a supernova, the release of energy and the scattering of matter further contributes to the universe's entropy. One of the most intriguing aspects of entropy is its connection to the fate of the universe itself. Many scientists believe that the eventual end of the universe will be marked by the heat death, a state of maximum entropy where all matter and energy are evenly distributed, and no thermodynamic work can be done. In such a universe, there would be no gradients, no movement, no life. Everything would be in perfect equilibrium. The concept of heat death represents the ultimate expression of entropy's power, a universe where time, in its conventional sense, ceases to have any meaningful distinction. It would be a static, frozen existence, where no further change is possible. In this sense, the heat death of the universe is the end of not just life, but of the very fabric of time itself. Yet, even in this stark, seemingly inevitable end, there is a sense of profound beauty in the way entropy shapes the cosmos. The very fact that we can understand the law of entropy and the arrow of time is a testament to the incredible complexity and order that emerges, however briefly, within the chaotic universe. We, as humans, are transient products of this cosmic dance. Our consciousness, our thoughts, and our creations are all fleeting moments in the grand scheme of things. But these moments, though temporary, are intensely meaningful. They represent pockets of order that arise within the broader, inevitable tide of disorder. Our lives are flashes of brilliance against the backdrop of the cosmos, and our awareness of the passage of time, of the relentless increase of entropy, makes our experiences all the more precious. The tension between order and disorder, between life and entropy, is what drives much of human creativity. The artist, the scientist, the philosopher, all are engaged in a struggle to impose order on chaos, to make sense of a universe that constantly threatens to undo their efforts. Whether it's a work of art that seeks to capture the fleeting beauty of a moment, or a scientific theory that tries to uncover the underlying order of the cosmos, human endeavor is a testament to the desire to defy entropy, if only for a short while. Even the most mundane actions we take, from building a house to writing a poem, are efforts to impose meaning and structure on a world that is constantly sliding toward disorder. However, it is important to remember that entropy does not necessarily imply chaos in a negative sense. The universe's increasing entropy is simply a reflection of the way in which energy and matter are distributed and transformed. It's not a force with intent or malice, but a natural consequence of the laws of thermodynamics. Entropy, in this light, is neither good nor evil. It is simply the way the universe works. It is the price of complexity, the cost of existence itself. Without entropy, there would be no stars, no galaxies, no life. The unfolding of time, with all its disorder and unpredictability, is what allows for the creation of meaning, of beauty, of consciousness. Without the flow of time and entropy, there could be no experience, no past to remember, no future to anticipate, and no present to live. Entropy is far more than a physical phenomenon. It is a concept that defines the very fabric of existence. From the cosmic scale of the universe to the microscopic world of atoms and molecules, from the creation of life to the unfolding of human experience, entropy governs it all. The arrow of time, driven by entropy, moves relentlessly forward, shaping everything it touches. And yet, in that very movement, in that relentless progression toward disorder, there is beauty, there is meaning. We are not merely passive observers of this process. We are active participants, creators, and destroyers in the cosmic dance of order and chaos. The understanding of entropy, of time's arrow, is not just an intellectual pursuit but a profound meditation on the nature of existence itself. As we contemplate the vastness of time and entropy's influence on the universe, we begin to see that our place in this grand dance is not just one of passivity but of interaction. From the birth of galaxies to the decay of subatomic particles, everything around us is involved in a slow, inexorable march toward greater entropy. This process does not discriminate. It touches every aspect of reality, from the most distant stars to the intricate workings of our own minds. Every object, every system, and every living organism is engaged in a constant struggle against the forces of disorder. This struggle is not merely a physical one, it is also deeply philosophical and existential. How do we reconcile our finite existence with a universe that seems to be perpetually dissolving into chaos? How do we create meaning, purpose, and value in a world that is, by its very nature, moving toward ultimate dissolution? At the heart of these questions lies the human condition, our awareness of our own fragility in the face of the vast, uncaring universe. Unlike the unyielding forces of entropy that we observe in the world around us, our lives are marked by consciousness, by the ability to reflect on our place in the cosmos and to make decisions that can alter the course of our lives, if only temporarily. This awareness of time's arrow, of the relentless increase in disorder, is what gives our lives a sense of urgency. It pushes us to create, to build, to leave a mark on the world before we, too, succumb to the inevitable pull of entropy. The human experience is a constant negotiation with time, a balancing act between our desire for stability and our recognition of the impermanence of all things. One fascinating aspect of entropy is its connection to the concept of life itself. Life, in its most fundamental sense, is a fight against entropy. Living organisms, from the simplest bacteria to the most complex mammals, maintain a state of low entropy by consuming energy and expelling waste. This process, known as metabolism, is how life resists the forces of disorder. By taking in energy from the environment, whether in the form of food, sunlight, or other sources, living beings maintain their structure and organization, delaying the inevitable rise in entropy that would otherwise result in decay and death. But this fight against entropy is not a permanent victory. Eventually, all living organisms succumb to the increasing entropy that governs the universe. Cells age, structures break down, and ultimately, all life returns to the same chaotic state from which it emerged. The universe, too, can be viewed as a living system, in the sense that it is constantly undergoing a process of transformation, moving from a state of high energy and low entropy, as in the early moments after the Big Bang, to a state of lower energy and higher entropy. This transformation, while seemingly leading to a future of heat-death, is also the process through which the universe creates the conditions for life and complexity to emerge. In this sense, entropy can be seen as both a creator and a destroyer, an essential force that drives the evolution of the cosmos, making life possible, and yet, eventually, leading to its inevitable demise. Another aspect of entropy that warrants attention is its relationship with the second law of thermodynamics. This law, which states that the total entropy of an isolated system can never decrease, is a fundamental principle of physics. It implies that, over time, systems tend to move toward a state of maximum disorder. However, this law also allows for temporary decreases in entropy within localized systems, as long as the overall entropy of the larger system increases. In living organisms, for example, the process of maintaining order within cells requires energy and results in a net increase in the entropy of the surroundings. This interplay between localized decreases in entropy and the overall increase in entropy is a key feature of the way the universe operates. It explains why we can have moments of apparent order and coherence, such as the formation of complex life forms or the creation of intricate structures, while still adhering to the overarching trend toward disorder. While the idea of entropy and the arrow of time can seem daunting or even depressing, it also offers a unique perspective on life and the universe. Rather than seeing entropy as something to be feared or avoided, we can choose to view it as an essential aspect of the cosmos that shapes and defines everything. Without entropy, there would be no change, no evolution, no creativity. There would be no distinction between the past, present, and future, and the universe would be a stagnant, unchanging place. Entropy is the engine of transformation, driving everything from the formation of stars to the evolution of species to the development of human culture. It is the force that makes time meaningful, that imbues the passage of moments with a sense of urgency and significance. In this light, entropy can be seen as a reminder of the preciousness of life. Every moment, every interaction, and every achievement is a brief, shining instance of order amidst the chaos. Our consciousness, our awareness of the passage of time, is a unique gift, a fleeting awareness that allows us to appreciate the beauty of the world around us and the preciousness of our existence. Entropy, in a sense, gives our lives meaning, not by taking it away, but by making every moment more valuable because of its impermanence. As we look to the future of the universe, the eventual increase in entropy will likely lead to a state where all matter is evenly distributed, and no energy gradients remain. This state, known as the heat death of the universe, represents the final culmination of the arrow of time. In such a universe, there would be no thermodynamic processes, no movement, and no life. But even in the face of this ultimate fate, the concept of entropy remains one of the most profound aspects of our understanding of the cosmos. It is a force that defines our existence, that shapes the course of events, and that gives us a sense of our place in the universe. Through the lens of entropy, we can gain a deeper appreciation for the fleeting nature of life, for the beauty of creation, and for the profound mystery that is time. Ultimately, entropy teaches us that nothing in the universe is permanent. From the birth of stars to the rise and fall of civilizations, everything is subject to the inexorable flow of time and the increase in disorder. But this realization is not a call to despair. Instead, it is an invitation to embrace the fleeting nature of existence, to cherish the moments of order and clarity that we experience, and to understand that our lives are part of a much larger, ever-evolving cosmic story. In the end, it is the very impermanence of life, the slow march toward entropy, that gives our existence meaning. The inevitability of entropy also forces us to confront some of the most profound questions about existence, time, and the universe. The idea that everything will one day come to an end, that every system will eventually break down, forces us to reckon with the transient nature of all things. Yet this is not a bleak observation. Rather, it is a profound realization that can shape how we live and think. When we accept that nothing lasts forever, we are encouraged to make the most of the time we have, to appreciate the fleeting beauty of moments, relationships, and experiences. Time, like entropy, flows relentlessly forward, but it is precisely this forward motion, this irreversible direction, that imbues life with its preciousness. In the grand cosmic scale, entropy also presents an opportunity for rebirth, transformation, and renewal. While the eventual heat death of the universe seems to be the end of everything, it is not the end in a traditional sense. Entropy does not necessarily equate to finality. It may simply represent a phase in a cycle that we do not yet understand. As the universe evolves, it is possible that new forms of order and complexity could emerge from the ashes of entropy. The mystery of this process, which transcends our current understanding, is what drives many of the most intriguing questions in cosmology, physics, and philosophy. We can observe entropy in everyday life, and it manifests in countless ways, from the way a building slowly deteriorates over time, to the way memories fade as years pass. These are all reminders that the forces of disorder are always at play in the world around us. Yet there is something oddly comforting about this constant state of flux. It suggests that life, in all its forms, is part of a much larger, interconnected process of creation and destruction. From the simplest organic molecules to the grand scale of galaxies, everything is engaged in a dance with entropy, resisting it for a time, but eventually surrendering to it. In physics, the study of entropy is not just limited to thermodynamics. It also plays a crucial role in understanding the flow of information. Entropy, in this sense, can be thought of as a measure of uncertainty or unpredictability within a system. The more uncertain or disordered a system is, the higher its entropy. This relationship between entropy and information has profound implications for fields ranging from information theory to quantum mechanics. In fact, one of the most famous thinkers on the subject, the physicist Claude Shannon, used the concept of entropy to define the amount of information in a message. A message with high entropy is one that contains more unpredictability and, therefore, more information. This connection between entropy and information has led to fascinating explorations into the ways that information is processed in the universe, from the functioning of computers to the behavior of particles at the quantum level. This connection also invites us to think about entropy in a more abstract way, as a fundamental aspect of the universe that extends beyond physical processes. If entropy governs the flow of energy and the decay of systems, could it also govern the flow of ideas, culture, and civilization? Just as physical systems inevitably move toward disorder, it is possible that human societies, too, face a similar trajectory. Civilizations rise and fall, ideas come and go, and even the most established systems eventually succumb to the forces of entropy. But again, this does not necessarily mean the end. It is simply a shift, a transformation into something new. In the collapse of one system, there is often the potential for the creation of another, just as the collapse of stars leads to the formation of new elements and galaxies. When we reflect on the passage of time, we must also confront the question of how we experience it. Time is not just an abstract concept, it is deeply intertwined with our perception of reality. Our lives are shaped by the way we experience the world, and this experience is inevitably influenced by entropy. As we grow older, we witness the gradual decay of our bodies, the fading of memories, and the loss of things we once held dear. This process of aging is a direct manifestation of the second law of thermodynamics, as our bodies, like all systems, are constantly moving toward greater disorder. Yet, even as our bodies age and decline, our minds have the ability to reflect on the passage of time. We can appreciate the beauty of the present moment, knowing that it will soon be a part of the past. This awareness of time's passage, of entropy in action, is part of what makes our lives meaningful. It is a recognition of the transience of all things that allows us to savor what we have while we have it. In a more scientific sense, time itself may be an illusion, a construct that arises from our perception of entropy. In the world of quantum mechanics, time does not behave in the linear, predictable way that we experience it. Particles exist in states of probability, and events do not unfold in a strict, chronological order. It is only when we observe these particles and measure their interactions that time, as we know it, begins to take shape. This raises the intriguing possibility that the arrow of time, the perception that time always flows in one direction, is actually a result of our limited perspective. If time is not truly linear, but instead is a product of entropy, then it may be a far more complex phenomenon than we currently understand. Perhaps our perception of time is merely a reflection of the way entropy manifests in our everyday lives, a consequence of our place in the vast and ever-changing cosmos. From a philosophical standpoint, the concept of entropy and the arrow of time challenges us to consider the nature of free will. If the universe is governed by the second law of thermodynamics, and everything inevitably moves toward disorder, where does human agency fit into this picture? Are we simply puppets of the universe, acting out our roles in a predetermined drama, or do we possess the ability to shape our own destinies? This tension between determinism and free will has been a topic of debate for centuries, and the relationship between entropy and the passage of time only adds another layer of complexity to this discussion. If the future is determined by the entropy of the present, can we truly make choices that alter the course of our lives, or are we simply riding the inevitable wave of disorder? In one sense, the arrow of time and the inevitable increase of entropy suggest that the universe operates according to a set of immutable laws. But in another sense, the presence of life, consciousness, and thought challenges this deterministic view. Conscious beings, like humans, are capable of introspection, creativity, and self-determination. We can recognize the forces of entropy at work around us, and within the limits of our biology and environment, we can choose to resist them, if only temporarily. This ability to influence the world, to impose order on the chaos, is one of the most remarkable aspects of life. It speaks to the profound potential that exists within each of us to make a difference in the world, even in the face of an ever-encroaching tide of disorder. Entropy, then, is not merely a physical principle that governs the behavior of matter and energy. It is a concept that speaks to the very nature of existence itself, an idea that stretches across the realms of science, philosophy, and human experience. It challenges us to confront the inevitable decline of all things, but it also invites us to appreciate the fleeting beauty of life, to create meaning in a universe that is constantly changing. The arrow of time, in all its complexity, is not just a scientific fact, it is a profound reminder of the impermanence of all things and the preciousness of the moments we have. As we continue to unravel the implications of entropy and the arrow of time, it's crucial to explore the connection between entropy and life itself. In many ways, life can be seen as a delicate balance between order and chaos. Organisms fight against entropy every day, At the biological level, this struggle is evident in the process of metabolism, where living organisms take in energy to maintain their complex, highly organized structures. Cells, tissues, and organs resist the natural decay of entropy by using energy to create and maintain order. But despite this ongoing battle, the inevitability of entropy still looms over every organism. Aging is, in many ways, a direct manifestation of entropy. As we age, our cells lose their ability to repair and regenerate, and our bodies gradually succumb to the disintegration of time. Yet, this gradual decline is not entirely devoid of meaning. The cycle of life, birth, death, and rebirth is a testament to the interconnectedness of all living things, as they contribute to the ongoing dance of entropy and renewal. When we look beyond the individual and consider ecosystems, we see that entropy plays a central role in the larger picture of ecological balance. Ecosystems, too, are constantly fighting against entropy. Through energy flow, primarily from the sun, living organisms maintain their intricate web of interactions. Plants convert sunlight into chemical energy through photosynthesis, animals consume plants and other animals, and decomposers break down organic matter, returning energy and nutrients back into the system. This complex interplay of order and disorder creates a dynamic equilibrium. However, ecosystems are not immune to the ravages of entropy. Natural disasters, changes in climate, or disruptions to the energy flow can upset the balance and push ecosystems toward greater disorder. Yet, even in this chaos, there is often the potential for renewal. Disturbed ecosystems can regenerate, adapting to new conditions and re-establishing a state of balance, albeit one that is different from the original state. The relationship between entropy and life invites us to reconsider our role in the universe. We are not mere passive observers of the passage of time. Instead, we are active participants in the ongoing process of creating order, meaning, and value. Our actions, thoughts, and experiences shape the world around us. In our daily lives, we constantly create and destroy, build and dismantle. The structures we create, whether physical or societal, are temporary, and their eventual decay is an inevitable consequence of the laws of entropy. But that does not mean they lack value. On the contrary, the very impermanence of life and human creations adds to their significance. Our ability to understand entropy gives us a deeper appreciation for the time we have and the ways in which we can resist the natural course of decay, even if only for a time. The impact of entropy is also evident in the realm of human culture. Just as physical systems tend toward disorder, the cultural artifacts we leave behind, whether art, literature, or architecture, are subject to the same forces of decay as any other physical object. Yet, despite this inevitability, these cultural expressions persist in some form, whether in museums, in memories, or in the ideas they inspire. The persistence of human culture, despite the ravages of entropy, suggests that even in a universe of constant decay, there is something enduring about the human experience, a desire to create, to communicate, and to leave a lasting legacy. This interplay between entropy and culture is particularly apparent when we consider the ways in which human societies grapple with the passage of time. Every civilization has sought to defy the forces of entropy in one way or another. The construction of monumental architecture, the preservation of historical records, and the creation of enduring symbols are all ways in which humans attempt to resist the inevitable decay of time. Even our most enduring works of art, literature, and philosophy are subject to the ravages of entropy. Yet, despite their physical deterioration, these works continue to exert influence, shaping the thoughts and actions of future generations. The persistence of ideas, the transmission of knowledge, and the continuous reinvention of culture suggest that while entropy may govern the material world, the human spirit has a remarkable ability to transcend it. As we turn to the cosmos, the scale of entropy becomes even more staggering. The universe, as we understand it, is constantly evolving toward a state of maximum entropy, what is often referred to as heat death. In this far-off future, all matter and energy will be uniformly distributed, and no useful work will be possible. Stars will burn out, galaxies will drift apart, and the universe will enter a state of unrelenting uniformity. The universe will be devoid of the structure and complexity that we observe today. However, this final state is not one of complete nothingness. Instead, it represents the ultimate equilibrium, a state where entropy has reached its maximum, and all systems are in perfect balance. This may sound like an end, but it is also a form of cosmic equilibrium, where all the processes that once drove the universe toward complexity and change have been played out. Interestingly, the study of entropy in the cosmos also raises questions about the nature of time itself. If the universe is ultimately moving toward a state of maximum entropy, this suggests that time is inherently tied to the flow of energy and the creation of order. In a universe of maximum entropy, there would be no energy gradients, and as a result, there would be no reason for time to flow in the way we experience it. Time, as we know it, would cease to exist. This raises fascinating questions about the nature of time and its relationship to the physical world. If time is a consequence of entropy, then understanding the laws of thermodynamics may hold the key to unlocking the deepest mysteries of time itself. The arrow of time and entropy also invite us to reflect on the ultimate fate of life, intelligence, and consciousness. If entropy is a fundamental law of nature, then it suggests that all systems, no matter how complex or organized, will eventually succumb to disorder. The question, then, is whether life and consciousness can persist in the face of this inevitable decay. Some theorists speculate that advanced civilizations may one day find ways to delay, or even reverse the effects of entropy, perhaps by harnessing the energy of black holes or manipulating the fabric of spacetime itself. Others suggest that consciousness may be able to transcend the physical world entirely, existing in a purely informational state, beyond the reach of entropy. These ideas, while speculative, point to the possibility that the human struggle against entropy may take on new forms in the future, as we seek to understand and navigate the ultimate forces of the universe. Entropy is not just a scientific concept, it is a profound and inevitable part of the human experience. It shapes the flow of time, the decay of our bodies, the rise and fall of civilizations, and the evolution of the cosmos. Yet, in the face of this inevitable decay, there is something deeply meaningful about our existence. It is in our awareness of entropy, our understanding of the fleeting nature of time, that we find the motivation to create, to love, to explore, and to seek meaning. The arrow of time, as it carries us toward an uncertain future, challenges us to live fully in the present and to cherish the moments we have. In doing so, we embrace the very essence of life, the ability to create order and meaning in a universe that is forever moving toward disorder. As we continue to dive deeper into the concept of entropy and the arrow of time, it's essential to recognize the profound implications this understanding has for our view of the universe. Entropy doesn't just play a role in the physical world, it extends to our perception of life, death, and even the way we understand meaning itself. When we think of time, we often think of it as a constant, something that ticks away uniformly. We wake up, experience the events of the day, and fall asleep, only to wake up again in the same cycle. But when we confront the concept of entropy, we realize that time is not just a constant flow, it's a flow defined by the inevitable direction towards disorder. What is even more intriguing is the idea that entropy, and thus time, has an arrow. This arrow of time refers to the fact that time always moves in one direction, from past to present to future. It's a one-way street, and it's a feature that defines our entire experience of the universe. Imagine for a moment if time didn't have this one-way direction, if it could flow backward. What would that look like? The possibility of time reversing itself is a concept that has fascinated scientists and philosophers alike. Some theories, like those in quantum mechanics, suggest that in certain conditions, time could theoretically move backward. But in the macroscopic world we experience, we see no evidence of time reversing its course. The most compelling reason for this forward movement is entropy. Entropy is tied intrinsically to the progression of time. The second law of thermodynamics, which states that entropy in an isolated system will always increase, effectively sets the stage for the forward flow of time. This law is not just a scientific principle, it's a fundamental truth about the universe. It is the reason we experience time as a sequence of events that cannot be undone. We can't rewind time, nor can we reverse the aging process. What's done is done, and in every moment, entropy pushes us further along the path of irreversible change. This brings us to the existential significance of entropy. The very fact that time flows in one direction, toward greater disorder, has led some to question the meaning of life itself. If everything, from stars to civilizations, from our bodies to our ideas, is destined to decay, is there any point to anything? It's a profound question. Some may find this thought depressing, but others may see it as liberating. If entropy is inevitable, and time can never be reversed, then it becomes all the more important to make the most of the time we have. It encourages us to find meaning in the present moment, to cherish the fleeting experiences and relationships that make up our lives. In a world where decay is a certainty, the beauty of life lies not in its permanence, but in its impermanence. Another fascinating aspect of entropy is how it influences the concept of death. Just as the universe itself will eventually reach a state of maximum entropy, so too will every living being. The human body, for example, is a highly organized system, constantly fighting against the forces of entropy. Our cells repair themselves, our bodies maintain homeostasis, and we grow and develop. But no matter how much we fight it, entropy is always at work. Cells age, accumulate damage, and eventually die. This process, known as senescence, is a direct consequence of entropy. It's a reminder that no matter how much we try to maintain order, the natural state of things is disorder. Yet, just as entropy defines the inevitable end of an individual life, it also provides the potential for renewal. Death is not simply an end, but a transition, an opportunity for new life to emerge. The decay of one organism nourishes others, and in this way, entropy facilitates the cycles of life. In nature, nothing truly disappears. It is transformed, broken down, and repurposed. From the decay of fallen leaves comes new soil for plants to grow. From the death of one star, a new one can be born. In this sense, entropy is not just about destruction, it is also about creation. It is the engine that drives the continuous renewal of the cosmos, the endless cycle of life, death, and rebirth. This understanding of entropy also challenges our perceptions of progress and advancement. In the context of human history, we often think of progress as a linear path forward, toward greater knowledge, more complex societies, and improved technologies. But this forward motion is not guaranteed. History is filled with periods of great civilizations collapsing, empires falling, and knowledge being lost. The rise of entropy within human civilizations can be seen in the decay of ancient ruins, the loss of knowledge, and the eventual disappearance of societies that once flourished. The rise of entropy is an ever-present force that ensures no civilization, no matter how advanced, can escape its reach. However, just as individual organisms resist entropy by consuming energy and maintaining order, human societies have developed ways to fight against the forces of decay. We have created systems of education, infrastructure, and cultural preservation that allow us to transmit knowledge across generations. We build monuments, write books, and record our stories, all in an effort to resist the march of time. But even in this, entropy is present. The very systems we create to preserve knowledge and culture are themselves subject to decay. Libraries burn, cities fall to ruin, and once great empires collapse. Yet, in the ashes of these civilizations, new societies often rise, learning from the past and continuing the cycle. In the realm of science and technology, we also encounter the paradox of entropy. Technology has allowed us to extend our lifespans, preserve knowledge, and even manipulate the natural world to a certain extent. But no matter how advanced our technology becomes, we cannot escape the fundamental truth of entropy. Machines break down, systems fail, and resources are depleted. Even in the digital age, with vast amounts of data stored in virtual realms, entropy is at work. Hard drives fail, websites go offline, and data is lost. The digital world, like the physical world, is subject to the forces of decay. And yet, as with the natural world, there is beauty in the struggle against entropy. It is this struggle that has driven human innovation and creativity. It is this struggle that gives our lives meaning. At a cosmic scale, the idea of entropy raises profound questions about the ultimate fate of the universe. As we peer into the vast expanse of space, we observe galaxies, stars, and nebulae in various stages of life and death. Some stars are just beginning to form, while others have burned out and become black holes. Over time, all matter in the universe will ultimately break down. Stars will burn through their fuel, galaxies will collide and merge, and black holes will eventually evaporate. The universe will cool, and all matter will be evenly distributed. The eventual state of the universe, when all processes have come to an end and no further work can be done, is what is known as the heat death of the universe. This is the ultimate expression of entropy, a universe in which all energy has been used up, and there is no longer any possibility for change or life. Yet, as bleak as this may sound, the heat death of the universe is not an end in the traditional sense. It is simply the final chapter in a long, drawn-out process of transformation. The universe, from its birth in the Big Bang to its eventual decay, will always be in motion, always changing, always shifting. Entropy ensures that there is no stasis, no absolute rest. Even in the far-flung future, as stars die and galaxies drift apart, the universe will still be evolving, even if that evolution is toward greater disorder. In many ways, entropy teaches us about the impermanence of everything in our lives. It is a force that cannot be escaped, a constant reminder that nothing lasts forever. But this realization can inspire us to live more fully in the present. If we understand that everything, from our bodies to our civilizations to the stars themselves, is subject to entropy, we might be more inclined to appreciate the moments we have. We may be more driven to create, to experience, to love, and to leave something meaningful behind. For in the end, it is the fight against entropy, the act of resisting decay, that makes our lives rich and worthwhile. In exploring the relationship between entropy and the arrow of time, we are not merely investigating a scientific principle. We are confronting the very nature of existence. The arrow of time is the sense that time flows in one direction, always moving forward, and its flow is governed by entropy. From the moment the Big Bang occurred, the universe began its journey toward greater disorder, and everything that exists has been carried along by this inexorable force ever since. But in considering this, we must also ask, does the arrow of time define more than just the physical world? Does it shape our experiences, our perceptions, and our actions in ways we don't even fully comprehend? There is an inherent tension in the human experience when it comes to time and entropy. We are bound by the laws of nature that ensure our lives are finite. Yet, within this framework, we also strive to create meaning, to leave behind legacies that defy the pull of entropy. We write books, build monuments, and invent technologies, each an attempt to freeze a moment in time, to make something that outlasts us. And yet, the more we try to resist entropy, the more we find that it is an inevitable force that slowly works to undo our efforts. This is why understanding the arrow of time is not just about the scientific principles behind entropy, but about the way it intertwines with the very core of human experience. This tension between order and chaos, between life and death, is something that has captivated thinkers for centuries. Ancient philosophers like Heraclitus recognized that everything is in constant flux, that the only constant in life is change. Modern scientists, too, recognize this idea, but with a much more specific understanding: change is driven by entropy. The universe is a dynamic system, and entropy ensures that it will never remain the same. But while this is a source of profound challenge, it also opens the door to possibilities. Entropy is not just about decay, it is also about transformation. The destruction of one form of order leads to the potential for something new to emerge. We see this in the natural world, where the decay of organic material feeds new life. In the cosmos, stars form, live, and die, and in their deaths, they give rise to new elements, new possibilities for life. Entropy ensures that nothing stays the same, but it also guarantees that everything can change. While this may seem like a paradox, something that brings about both decay and renewal, it reflects a deeper truth: entropy is the driver of progress, evolution, and growth. Consider the way we view technological progress. From the first tools used by early humans to the computers and smartphones we use today, human history has been marked by an unrelenting march forward in terms of technology. But as we push forward, entropy is always present in the background, reminding us that no technology will last forever. Devices break down, systems become obsolete, and new technologies arise to replace the old. In a sense, entropy is a fundamental driver behind innovation. We are constantly responding to the decay of the old by creating the new, by improving upon the past to meet the challenges of the present. But this cycle of creation and destruction is something that will never stop. The idea of entropy also brings a deeper understanding to the concept of life itself. All living organisms, from the simplest bacteria to the most complex human beings, are systems that resist entropy by constantly taking in energy from the environment. Our cells work tirelessly to maintain order, to repair damage, and to grow. This constant battle against entropy is what keeps us alive. But over time, this process becomes less efficient, and the body's resistance to entropy weakens. Aging is a direct consequence of this. Our bodies are not immune to the forces of disorder, and eventually, entropy wins. It's a humbling realization that even the most complex, organized systems we know, like living organisms, are subject to the same inevitable decay. However, the very fact that life exists in defiance of entropy is a remarkable feat in itself. It is a testament to the power of energy and the resilience of complex systems. Life is a phenomenon that operates in a delicate balance, constantly consuming energy to maintain order. But eventually, even the most finely tuned systems break down. This is not something to be feared, rather, it is something to be understood. Entropy teaches us the value of the present, the fragility of our existence, and the importance of cherishing the moments we have. In a way, entropy also reflects the impermanence of knowledge and culture. Our understanding of the universe has evolved over millennia, but each generation builds upon the knowledge of the past while confronting the decay of ideas that no longer serve us. In this sense, the arrow of time is not just a physical phenomenon, it is a social and intellectual one. Over time, societies rise and fall, ideas come and go, and entire civilizations can fade into obscurity. Yet, just as entropy ensures the transformation of physical matter, it also ensures that knowledge is never entirely lost. Even as one era ends, the foundations laid by those who came before us continue to shape the future. In scientific fields, we see this same process play out in the ongoing accumulation of knowledge. As new discoveries are made, older models are discarded or revised. But the old models, even in their obsolescence, serve as stepping stones to the new. This constant process of discovery and rediscovery is an expression of the forward flow of time. And just like the rest of the universe, scientific progress is subject to the forces of entropy. No system of knowledge or technology is immune to decay. But each new generation of scientists builds on the achievements of those who came before them, creating a continuous chain of progress that stretches into the future. The concept of the arrow of time and entropy also gives us a unique perspective on the future. We often think of the future as something that is full of potential, full of possibilities. But what if the future is also defined by the same forces that shape the present and the past? If entropy is always increasing, and if the arrow of time is always pointing forward, then the future may not be as full of potential as we like to think. As entropy increases, the amount of usable energy decreases, and with it, the potential for growth and progress. The future may eventually become a place where life, as we understand it, is no longer possible. But rather than viewing this as a bleak future, we should see it as part of the natural course of things. Just as stars are born, live, and die, so too do the systems and structures we build. The eventual heat death of the universe, when all energy is evenly distributed and no work can be done, is simply the final chapter in the ongoing story of the cosmos. It is not an end, but a transformation, a return to the primordial state from which everything began. In the same way, the eventual decay of life and society is not an end, but a part of the greater cycle of existence. In the face of entropy, we may feel helpless, as if we are powerless against the forces of nature. But the truth is that we are part of the grand scheme of things, each of us playing a role in the ongoing dance between order and disorder. It is the very existence of life, of consciousness, thought, and action, that gives meaning to the universe. And as long as we are aware of this, we can continue to create, to learn, to grow, and to leave a legacy that defies the decay of time. Entropy may be the force that pushes us toward disorder, but it is also the force that enables us to create, to transform, and to transcend. As we continue exploring the vast implications of entropy and the arrow of time, we are reminded that the seemingly abstract principles we study in physics also reverberate in our everyday experiences. Time is often seen as an abstract concept, something that flows in the background of our existence. But when we delve deeper into the science of time and entropy, it becomes clear that these forces shape not only the physical world but also our very perceptions of reality. Our sense of past, present, and future is grounded in the flow of time, and as time passes, entropy relentlessly increases, pulling all things toward inevitable decay. One of the most intriguing aspects of the arrow of time is the way it intersects with human consciousness. We experience time as a linear, forward-moving force. Events unfold, one after the other, and we are unable to reverse this process. This perception is deeply ingrained in us, and it influences how we live our lives. We plan for the future, learn from the past, and attempt to live in the present, all under the awareness that time is finite, always moving forward. Yet, despite this inevitability, we constantly seek to resist the effects of time. We try to preserve moments, memories, and achievements. We photograph and document our lives, seeking to freeze fleeting moments and keep them intact. We attempt to escape the ravages of time through technology, all the while knowing that entropy remains the silent companion to every attempt at preservation. The way we view memory is an excellent example of how entropy and the arrow of time shape our understanding of the world. Memory is our link to the past, a means of retaining and processing information that shapes our identity and informs our decisions. However, memories are not static, they degrade over time. As our brains store and recall information, entropy gradually affects the accuracy and clarity of those memories. This gradual decay leads to the fading of details, the loss of sharpness, and the blurring of experiences. The more time passes, the more memories can become distorted, leaving us with a sense that the past is not as clear as we once thought. Even our most cherished recollections, once vivid and precise, can slip through our fingers as entropy works its subtle magic. This connection between memory and entropy highlights the complex relationship between the physical world and our subjective experience of time. While entropy operates on a universal scale, shaping the fate of the cosmos, it also infiltrates the realm of human consciousness. Just as the stars burn out and the universe moves toward greater disorder, our own minds are not immune to the effects of time. Yet, in this very vulnerability lies a paradox. As the universe grows older and entropy increases, life and consciousness persist, finding meaning and significance within a world that is slowly, inevitably, losing its energy. This struggle between decay and creation, between order and chaos, is what defines much of the human experience. Furthermore, the concept of entropy forces us to confront the fundamental nature of time itself. The second law of thermodynamics tells us that entropy must always increase, but this rule only applies within the confines of our universe. The universe, as a closed system, is locked into a process that moves relentlessly toward disorder. However, what lies beyond this closed system? Does time continue in some form outside the bounds of the universe? Could the arrow of time be a feature of the universe itself, or is it something more profound, extending into realms we have yet to understand? The idea that the arrow of time is inextricably linked to entropy raises questions not only about the future of the universe but also about the fundamental structure of reality itself. In some ways, the very existence of time may be a product of the increasing disorder that governs the cosmos. Without entropy, would we even have a concept of time? Could time exist in a perfectly ordered, static universe where nothing ever changed? This leads us into the realm of speculation, where the boundaries of known science meet the limits of human imagination. One such speculation involves the potential for reversing the arrow of time. Some scientists have proposed theories that suggest it may be possible to manipulate time in such a way that the flow of entropy could be reversed, at least locally. This idea, while intriguing, faces tremendous challenges. it would require not only vast amounts of energy but also an entirely new understanding of the laws of physics. If time could be reversed, what would it mean for the universe? Would it simply return to a state of greater order, or would the universe evolve in an entirely different way? While these questions remain unanswered, they highlight the vastness of our ignorance and the limits of current scientific understanding. One fascinating aspect of these speculations is the role of black holes in the universe. Black holes are regions of spacetime where the gravitational pull is so intense that nothing, not even light, can escape. These mysterious objects are thought to play a central role in the evolution of the universe, and some scientists have theorized that they may hold the key to understanding the nature of time itself. For example, the idea of time dilation, where time slows down in the presence of intense gravitational fields, suggests that the flow of time is not absolute but is dependent on the curvature of spacetime. In regions near a black hole, time may flow more slowly, offering the tantalizing possibility of exploring different versions of time. At the same time, the study of black holes also deepens our understanding of entropy. In fact, black holes have been described as the most efficient entropy generators in the universe. The famous equation known as the Bekenstein-Hawking entropy quantifies the amount of information, or entropy, that is contained within a black hole. This equation reveals that the entropy of a black hole is proportional to the surface area of its event horizon, not its volume. This counterintuitive result suggests that black holes may be the ultimate expression of entropy, where the highest degree of disorder is concentrated in the smallest possible region of space. The connection between black holes and entropy has profound implications for our understanding of the universe. It suggests that the cosmos may not be a static, orderly place but rather a dynamic, ever-changing system where entropy drives the evolution of everything, from the smallest particles to the largest cosmic structures. In this sense, the arrow of time and entropy are not just abstract concepts, they are fundamental to the very fabric of reality, shaping the universe in ways we are only beginning to understand. As we continue to explore the relationship between entropy, the arrow of time, and the nature of existence, we are faced with the humbling realization that much of what we take for granted, our perception of time, the flow of events, and the progression of life, may be deeply intertwined with forces beyond our control. Entropy reminds us that all things, from the stars to our own lives, are subject to decay and transformation. Yet, in this process of decay, we find new opportunities for growth, renewal, and change. Time, as it moves inexorably forward, carries with it both the promise of loss and the possibility of discovery. And in the end, it is this very tension, between order and disorder, between creation and destruction, that makes the story of the universe so profoundly compelling. As we continue to explore the relationship between entropy and the arrow of time, it becomes increasingly apparent that these concepts are not only fundamental to understanding the physical world but also offer deeper insights into the human experience. The arrow of time, with its unidirectional flow, creates a framework in which we live our lives, a framework that is governed by the relentless increase in entropy. This increase in entropy is not just a physical law, it is a lens through which we can examine the broader aspects of existence, from the cosmos to the small, fleeting moments of our lives. At the most fundamental level, the second law of thermodynamics, which dictates that entropy must increase in a closed system, serves as a kind of cosmic clock. Time, in this sense, is not merely an abstract dimension in which events occur, it is inherently tied to the movement toward disorder. Every interaction, every physical process, contributes to the steady march of entropy. The universe, in all its complexity, is in a constant state of transformation. Stars are born, burn out, and die, galaxies collide and merge, and on a microscopic level, atoms constantly undergo chemical reactions that lead to the release of energy. This is the dance of entropy, the unfolding story of a universe that is always becoming more disordered, more chaotic. Yet, within this overwhelming sense of inevitability, there is a curious paradox. Despite the increase in entropy, life persists. Life, with its remarkable ability to resist entropy locally, stands as a testament to the power of creation in the face of decay. Living organisms, from the simplest bacteria to the most complex human beings, are systems that maintain a high degree of order within themselves. Through processes such as metabolism and adaptation, life seems to defy the pull of entropy. But this resistance is temporary. Eventually, every living system succumbs to the inevitable march of time, and entropy takes its toll. This tension between life and entropy is perhaps most poignantly illustrated in the aging process. As we age, our bodies slowly lose their ability to maintain order. Cells stop functioning as efficiently, and the structures that keep our bodies intact begin to degrade. This process is an intimate reminder that even the most complex and sophisticated systems, our bodies, our societies, our civilizations, are ultimately governed by the laws of thermodynamics. The arrow of time, through its unrelenting increase in entropy, leads all things toward an eventual state of equilibrium, where disorder reigns supreme. However, despite this inevitability, human beings have developed remarkable ways of navigating the flow of time. Through technology, culture, and science, we have managed to extend our lifespans, preserve our memories, and even record our experiences for future generations. While we cannot escape the fundamental laws of physics, we have found ways to push back against the tide of entropy, if only for a short time. The invention of writing, for example, allowed us to store information across generations, defying the natural decay of memory. Photography and film capture moments that would otherwise be lost to the passage of time, offering a glimpse of eternity. Our ability to create art, music, and literature allows us to leave our mark on the world, even after our physical bodies are gone. At a deeper level, the struggle against entropy is not just a physical endeavor, it is a philosophical and existential one. Human beings have long grappled with the concept of mortality, seeking ways to understand and transcend the limitations of time. In the realm of physics, the study of entropy and the arrow of time raises profound questions about the nature of the universe itself. What is the ultimate fate of the cosmos? If entropy continues to increase, will the universe eventually reach a state of maximum disorder, where no energy is available to do work? This scenario, known as the heat death of the universe, is one of the most widely accepted predictions for the ultimate end of the cosmos. In this state, all matter and energy would be uniformly distributed, and there would be no gradients of temperature or pressure to drive physical processes. The universe would become a cold, dark, lifeless expanse. Yet, this is not the only possible fate for the universe. Some theories suggest that the universe could undergo a big crunch, where the expansion of space reverses and everything collapses back into a singularity. In this scenario, time would reverse, and the arrow of time would point inward, leading to a state of maximum order. However, this theory is still speculative, and recent observations suggest that the expansion of the universe is accelerating, making the big crunch increasingly unlikely. Another possibility is that the universe could experience a big rip, where the fabric of space-time itself is torn apart by the acceleration of cosmic expansion. In this scenario, galaxies, stars, planets, and even atoms would be pulled apart as the forces of entropy overwhelm the structure of the universe. While this scenario is still theoretical, it highlights the unpredictable and sometimes chaotic nature of the cosmos. The fate of the universe, like the fate of all things, remains uncertain, and entropy is the only certainty we can rely on. These cosmic speculations are not just abstract exercises in theoretical physics. They offer profound insights into the nature of existence. The ultimate fate of the universe, like the ultimate fate of all living things, is shaped by the inexorable laws of thermodynamics. Entropy is the force that drives the universe toward its inevitable end, yet it is also the force that shapes the very nature of existence. Life, time, and the universe itself are all subject to the same cosmic forces that govern the movement of particles and the behavior of energy. In this way, the study of entropy and the arrow of time is not just a study of the physical world but a study of the deeper mysteries of existence. As we reach the limits of our understanding, we are confronted with the profound realization that entropy is not just a force of destruction, but also one of creation. From the Big Bang to the formation of stars and galaxies, the universe has evolved through a process of increasing disorder, but it is through this very process that the complexity of life and consciousness has emerged. Entropy, in its relentless pursuit of disorder, has created the conditions for the emergence of life, thought, and experience. In this sense, entropy is not merely a force of decay, but one of transformation, a force that continually reshapes the universe, giving rise to new possibilities and new forms of existence. In our own lives, we see this dynamic play out in the small moments of everyday existence. Time passes, things change, and entropy does its work, but in the midst of this decay, we find opportunities for growth, creativity, and meaning. Whether it is the development of new technologies, the creation of art, or the formation of relationships, human beings continue to push back against the tide of entropy, finding ways to preserve what is valuable and meaningful. It is this ability to create and to find meaning in a world governed by decay that makes the human experience so extraordinary. As we look to the future, we are left to wonder, what lies beyond the limits of entropy? Is there a way to escape the confines of time and disorder, or is the arrow of time destined to carry us all toward an inevitable end? The answers to these questions may lie beyond the reach of our current understanding, but one thing is certain: the study of entropy and the arrow of time will continue to shape our exploration of the cosmos, of life, and of the mysteries of existence itself. As we continue our journey into the depths of entropy and the arrow of time, the deeper we explore, the more we begin to realize the profound implications these concepts have not only on the physical world but on our very understanding of existence. From the smallest atomic particles to the vast stretches of the cosmos, entropy touches everything. It's the invisible hand that shapes the course of the universe, guiding it from one moment to the next in a steady, irreversible march. Yet, for all its dominance, entropy is not simply a force of decay or destruction. It is also a force of creation, as it gives rise to the complexity, beauty, and life we see around us. As we've seen, one of the most critical elements of the second law of thermodynamics is its requirement that entropy increase over time. This increasing disorder means that the universe is steadily evolving toward a state of maximum entropy. But what does this state really look like? It's a complex question, and the answer isn't easy. Some scientists envision this end state as a universe where all matter and energy are evenly distributed, with no gradients of temperature or pressure left to drive physical processes. In such a scenario, everything would be frozen in place, motionless, devoid of life or any meaningful interactions. The idea of the heat death of the universe represents one such interpretation of the eventual fate of the cosmos. In this vision, as the universe expands and stars burn out, the energy that once fueled the formation of galaxies and life will dissipate into the vastness of space. With no energy left to power the mechanisms of life, the universe will reach a state of complete equilibrium, where everything is uniformly cold and dark. This concept of heat death brings into sharp focus the relentless and inescapable nature of entropy. The universe, in this scenario, doesn't simply slow down. It eventually reaches a point where all change ceases, and no further work can be done. Yet, the idea of heat death, while intriguing, is not the only possible outcome for the universe. In fact, it might not even be the most probable. Recent discoveries, especially the observation of accelerated cosmic expansion, suggest that the universe is expanding at an increasingly rapid pace. This acceleration challenges the notion of a Big Crunch, where gravitational forces might eventually slow the universe's expansion and lead to a collapse. Instead, the universe may continue expanding indefinitely, eventually resulting in the Big Rip, a scenario where the very fabric of space-time tears apart under the influence of dark energy, a mysterious force that seems to be driving this acceleration. In this case, the universe's expansion doesn't just slow down, it reaches a point where galaxies, stars, planets, and even atoms themselves are torn apart by the overwhelming force of entropy. However, before we dive further into these cosmic scenarios, it's worth taking a step back and considering how entropy influences life on Earth, particularly through the lens of biology. The second law of thermodynamics is often viewed as a universal principle that applies to everything from the smallest subatomic particles to the largest galactic structures. But living organisms provide a fascinating counterpoint to this view. Despite the universal tendency toward increasing disorder, life exhibits a remarkable capacity to maintain order. Organisms are highly ordered systems, constantly working to resist the chaos of entropy. Through metabolic processes, cells maintain a level of organization, ensuring that the components necessary for life, proteins, enzymes, DNA, remain intact and functional. At the level of the organism, life continually imports energy, breaking down food and converting it into usable forms of work. In this way, life fights back against entropy, temporarily creating pockets of order within a universe that is otherwise becoming more disordered. But crucially, this resistance to entropy is not without cost. The process of maintaining order within living systems itself generates entropy, particularly in the form of waste heat, which is released into the environment. Thus, while life appears to resist entropy in some ways, it also contributes to the overall increase of disorder in the universe. This dynamic is particularly evident when we look at the life cycle of living organisms. From birth to death, every organism is engaged in a continuous process of maintaining order within itself, and this requires a constant input of energy. Over time, however, the ability of an organism to maintain this order begins to decline. The process of aging can be understood as the gradual breakdown of the body's ability to resist entropy. Cells lose their capacity for repair, and systems become less efficient. Eventually, the accumulation of entropy within the organism becomes too great to overcome, leading to death. Yet, even in death, entropy is not defeated. Rather, death marks the beginning of a new phase in the cycle of entropy. Once an organism dies, its components begin to decompose. The energy contained within the body is released into the environment, and the components of the organism are broken down into simpler substances. In this way, entropy continues its relentless march forward, turning complex, organized systems into simpler, disordered ones. Despite the inevitable influence of entropy, life's resilience in the face of it is remarkable. It is through life that we experience time in a way that feels meaningful and rich. We create memories, build relationships, and create art, all in an attempt to impose meaning and order on the otherwise chaotic flow of time. Time, for living beings, is not just a physical dimension, it is something we experience deeply, with each moment offering an opportunity for creation, growth, and discovery. And yet, the specter of entropy looms over us, reminding us that all things, including ourselves, are subject to the ravages of time. No matter how much we might try to resist or postpone it, entropy will eventually catch up with us. As we reach the end of our lives, the slow march of entropy becomes ever more apparent. Our bodies, once capable of resisting the pull of disorder, begin to succumb to it. The same forces that govern the growth and development of life also govern its decay. And this decay, in turn, contributes to the ongoing increase of entropy in the universe. Just as the stars, galaxies, and planets are destined to burn out, so too are our bodies. The difference, of course, is that we are conscious of our own entropy. We know that our time is limited, and it is this awareness that gives life its poignancy. In a cosmic sense, our individual lives are but tiny blips in the vast expanse of time. Yet, within those fleeting moments, we have the opportunity to create, to shape the world around us, and to leave our mark on history. Our actions, our choices, and our creations can transcend the boundaries of time and entropy, even if only for a moment. And this, perhaps, is where the true beauty of life lies. Though we may be subject to the inexorable forces of entropy, we can still find ways to create meaning, to resist chaos, and to push back against the overwhelming tide of disorder. In doing so, we embrace the paradox of existence, that life and time are both fleeting and eternal, both ordered and disordered, both created and destroyed by the very forces that govern the universe. As we continue to explore the relationship between entropy and the arrow of time, we are left with more questions than answers. What does the future hold for the universe? Will it continue to expand forever, or will it eventually collapse? Can life, in its many forms, continue to resist entropy indefinitely? And what, ultimately, is the role of human beings in this grand cosmic drama? These questions, while unanswerable for now, speak to the deepest mysteries of existence. They invite us to reflect on the nature of time, of life, and of the universe itself. And in contemplating these questions, we are reminded that, even in the face of entropy, there is beauty, meaning, and mystery to be found in the journey of life. As we venture deeper into the intricate relationship between entropy and the arrow of time, one key realization becomes clear. The two concepts are not just abstract theories but foundational forces that shape our reality. The idea of entropy, a measure of disorder or randomness, is intertwined with time in ways that go beyond the simple observation of decay or aging. It reveals something much more profound about the nature of existence itself. The passage of time is not merely the ticking of a clock, it is an unfolding process, a relentless progression toward increased disorder, governed by the second law of thermodynamics. This law states that in any isolated system, the total entropy will never decrease. Instead, it will either stay the same or increase. This simple, yet powerful principle drives the evolution of all natural processes, from the formation of stars to the decay of matter. In this light, time and entropy appear almost inseparable, as if the very nature of time itself is defined by the way entropy behaves. Every second that passes is marked by the increasing disorganization of the universe, a shift towards states of greater disorder. It's this gradual increase in entropy that makes time appear to move forward. In other words, time's arrow is pointing in one direction, toward greater disorder. The symmetry of time, which might suggest that the future is no different from the past, is broken by the one-way march of entropy. This irreversible flow of time is what makes the universe dynamic, ever-changing, and full of potential. Without entropy, time would lose its direction, and the cosmos would be stuck in a static, unchanging state. But while the increase of entropy might seem like a force of destruction, it also has a more subtle, creative role. Consider the fact that the complexity of life itself relies on the local decrease of entropy within specific systems, like cells, organisms, and ecosystems. While entropy increases in the universe as a whole, pockets of low-entropy systems emerge, allowing life to thrive. These systems, from the microscopic level of molecules to the macroscopic world of ecosystems, create a balance between order and disorder. Life, in a sense, is a temporary defiance of the overarching laws of entropy, yet it too must eventually succumb to these laws. This paradox, where life and death are inextricably linked to the ongoing increase in entropy, is what gives rise to the continuous cycle of birth, decay, and rebirth that we see throughout nature. Interestingly, the role of entropy in the evolution of the cosmos is not limited to the decay of matter and energy. It also plays a central part in the creation of structure and complexity. The very processes that lead to the death of stars, their eventual collapse and explosion into supernovae, are also the processes that give rise to new elements, new matter, and new stars. In a sense, entropy is responsible for the creation of the building blocks of the universe, even as it leads to the destruction of individual stars and galaxies. The death of one star can give birth to new stars, planets, and potentially, new forms of life. This cyclical process, where entropy drives both destruction and creation, mirrors the cycle of life itself. Furthermore, entropy and time are not merely concepts that exist on a cosmic scale. They have tangible implications in our everyday lives. Consider the way we experience the passage of time. As we age, our bodies undergo a process of increasing entropy. Our cells accumulate damage, our organs lose their efficiency, and we slowly become more susceptible to disease. The gradual breakdown of our bodies is a stark reminder that entropy is not just a theoretical concept, it is a personal, inevitable process. However, this aging process is not simply a decline, it is also an intricate dance of renewal and decay. While our bodies experience the ravages of entropy, they also repair themselves, adapt, and evolve, maintaining a delicate balance between order and chaos. The relationship between entropy and life's complexity is also reflected in the natural world. Ecosystems are systems of intricate interdependence, where the flow of energy through food chains creates a web of life. In these ecosystems, entropy is constantly at work, breaking down matter and recycling energy. Yet, within this system, the living organisms create local pockets of order, using energy to build complex structures and systems. In a way, life is an ongoing battle against the forces of entropy, one that requires a constant input of energy to maintain the delicate balance of order and disorder. This balance, however, is not static. Over time, ecosystems evolve, with species emerging, adapting, and eventually becoming extinct, as the natural cycles of entropy continue to shape the course of life. Another area where entropy and time play a crucial role is in the field of information theory. Information, whether encoded in DNA, stored in computers, or transmitted through communication systems, is fundamentally tied to the concept of entropy. In this context, entropy refers to the amount of uncertainty or disorder in a system. The more information is stored or transmitted, the more entropy is involved in its encoding and decoding. Information systems, whether biological or artificial, constantly fight against entropy by maintaining the structure and coherence of the data they carry. Yet, just as in the physical world, the accumulation of entropy can lead to the loss of information, whether through data corruption or the eventual death of the systems that store it. The relationship between entropy and information is yet another example of how the laws of thermodynamics shape not only the physical universe but also the way we understand and process the world around us. One of the most intriguing questions that arises from the study of entropy and the arrow of time is the nature of time itself. Is time truly a fundamental aspect of the universe, or is it merely a byproduct of entropy? The answer to this question is not immediately clear. Time, as we experience it, seems to flow in one direction, from past to present to future. But why should this be so? Could time, in fact, be an emergent property of the increase in entropy? Some physicists propose that time, as we know it, is not an intrinsic part of the fabric of the universe, but rather a result of the way entropy manifests itself. In this view, time is a human construct, a way of understanding the progression of events as entropy unfolds. This perspective challenges our intuitive understanding of time as something absolute and unchanging, suggesting instead that time is just a reflection of the underlying physical processes that govern the universe. As we continue to delve into these complex ideas, it's clear that the relationship between entropy, time, and life is anything but simple. From the cosmic scale to the biological level, entropy shapes the way the universe evolves, creating both disorder and order in a never-ending cycle. The arrow of time points in one direction, but that direction is not purely destructive, it is also creative, as entropy fosters the formation of new structures, new stars, and new forms of life. Yet, at the same time, entropy reminds us of the ultimate fate that awaits all things. Whether in the distant future of the universe or in the short lives of individual organisms, entropy will eventually triumph, bringing about the end of everything we know. But perhaps it's this very inevitability that makes the existence of life so precious. For in the face of entropy's relentless march, we have the ability to create meaning, to forge connections, and to build something that lasts, even if only for a moment. Time may be a river, flowing toward the inevitable increase of entropy, but in that flow, we have the opportunity to shape our destiny, to resist the tide, and to leave our mark on the universe. The unfolding journey of entropy and time continues to unfold layers that challenge and deepen our understanding of existence. As we examine the nature of time, it becomes increasingly clear that the arrow of time is not just a physical phenomenon, but also a concept embedded within the very fabric of our perceptions. Time moves forward, not merely because of the ticking of a clock or the rotation of the Earth, but because of entropy's inevitable push toward greater disorder. The passage of time is, in essence, a reflection of the laws of thermodynamics at work, but it also speaks to the very essence of how we experience the universe. Our subjective experience of time is deeply influenced by this progression from order to disorder, from complexity to simplicity. The concept of the arrow of time, coined by the British physicist Arthur Eddington in the early 20th century, helps us understand why we experience time as moving in one direction, from past to present to future. According to Eddington, the directionality of time is inherently tied to the second law of thermodynamics, which states that the total entropy of an isolated system will always increase over time. This law explains why we don't see objects spontaneously move from disorder to order, or why we can't unbreak an egg once it's been cracked. It also ties into our understanding of causality, the idea that events in the present are caused by events in the past, and in turn, will influence the future. The progression of entropy ensures that causality remains a consistent feature of our universe, establishing a flow that is irreversible. This irreversibility is perhaps the most striking feature of the arrow of time. Whether we're contemplating the death of stars, the aging of living organisms, or the decay of matter itself, we cannot reverse the process. We are not merely passive observers in this grand cosmic drama, either. Our lives, too, are bound by the constraints of entropy. As time marches forward, we too experience the gradual accumulation of entropy in our bodies and in the world around us. From the moment we are born, we are participants in a continuous process of change and decay, and ultimately, we too will succumb to the forces of entropy. The bodies we inhabit will break down, our cells will wear out, and our minds will falter. This inevitability, however, does not lead to hopelessness. The recognition that entropy is the fundamental driver of time can be an empowering realization, as it illuminates the preciousness of the present moment. While we cannot escape the eventual increase in entropy, we can choose how we live within it. It is precisely because we are aware of the fleeting nature of time that we are driven to create, to build, and to find meaning in the face of inevitable decay. The recognition of entropy's influence does not rob life of its value, rather, it enhances it. Time becomes all the more precious because we know it is a limited resource, and every moment is an opportunity to make an impact, to change the course of our lives, and to connect with others in meaningful ways. Moreover, the interplay between entropy and time is not confined to the biological or physical realms alone. It extends to the way we think, create, and experience the world. The very act of learning is an exercise in reducing entropy, at least in a localized sense. When we acquire new knowledge, we take a disordered system, the chaos of the unknown, and impose structure upon it. We form connections, recognize patterns, and create understanding where there was once confusion. In this sense, our consciousness is constantly fighting against the tide of entropy, constructing order from disorder in an attempt to make sense of the world. But even our thoughts are not immune to the ravages of time. Just as our bodies age, so too do our minds. Memories fade, neural connections weaken, and the clarity of thought we once enjoyed begins to diminish. The entropy of our minds, much like the entropy of the physical world, progresses relentlessly forward, altering the very essence of who we are. As we explore the vast implications of entropy, it's important to remember that it's not simply a force that brings about decay and destruction. It is also the force that brings about change and transformation. The creation of new stars, the formation of complex molecules, the emergence of life itself, all of these are products of entropy's workings. The universe, in its constant struggle with entropy, has given rise to the complexity we witness today. Even as the universe heads toward eventual heat death, with the ultimate increase of entropy and the cessation of all thermodynamic activity, the very processes that lead to that state also give birth to incredible phenomena. Stars are born, galaxies collide, and life emerges in the most unlikely of places. In fact, the very concept of life might be seen as a temporary defiance of entropy's relentless pull. Life forms, from the simplest microorganisms to the most complex organisms, maintain an astonishing degree of order within themselves, resisting the increase in entropy through the constant input of energy. It is only through this constant influx of energy, through food, sunlight, or other forms of sustenance, that life can continue to thrive, grow, and evolve. But this resistance to entropy is not permanent. Eventually, all life forms reach their entropy-driven limit and succumb to the inevitable forces of decay. This cycle of life and death, growth and decay, mirrors the larger cycle of the universe itself. In the context of cosmology, entropy also provides an essential framework for understanding the fate of the universe. The second law of thermodynamics is a key factor in predictions about the universe's long-term future. As stars burn through their fuel, they reach a point where they can no longer maintain their fusion processes, leading to their collapse or explosion. This marks the end of the star's life and contributes to the overall increase in entropy. Over billions of years, this process continues to unfold, with stars dying and new ones forming, only to eventually meet the same fate. As the universe ages, it will continue to move toward a state of maximum entropy, a state in which all energy is evenly distributed, and no thermodynamic processes can take place. This eventual heat death of the universe is a concept that has captivated scientists and philosophers alike, as it represents the ultimate endpoint of entropy's work. Yet, even within the confines of this seemingly inevitable end, there is room for exploration and wonder. The very fact that we can ponder these questions, that we can contemplate the nature of time and entropy, is a testament to the complexity and beauty of existence. The universe, in all its vastness and complexity, is shaped by forces far beyond our understanding. And yet, through the lens of entropy, we can begin to glimpse the intricate patterns that govern the cosmos. We can see how time flows, how entropy increases, and how all things are inextricably linked in this grand cosmic dance. As we move forward in this exploration of entropy, it's clear that there is much more to uncover about the relationship between time, disorder, and the universe. But one thing remains certain: the arrow of time will continue its march forward, carrying with it the forces of change, decay, and transformation. Whether we are contemplating the distant future of the cosmos or the quiet, inevitable aging of our own bodies, entropy reminds us of the impermanence of all things. Yet it also reminds us of the beauty and complexity that arise from this impermanence, urging us to embrace the present moment and to find meaning in the fleeting passage of time. As we continue to unpack the concepts of entropy and the arrow of time, it becomes evident that these ideas aren't just academic. They have profound implications on how we view our place in the universe. The universe's relentless march toward disorder doesn't just affect the stars or distant galaxies. It also shapes the way we experience our daily lives. The passage of time is inextricably tied to the flow of entropy, and as a result, everything in our world, from the smallest particles to the largest celestial bodies, is subject to the same laws. The very nature of existence is influenced by this gradual, inevitable process of disorder. Whether it's the gradual aging of a human body or the slow collapse of a massive star, time and entropy remind us that change is constant, and nothing remains static. However, despite this seemingly relentless march toward disorder, there's an interesting aspect of the entropy process. It's not all about decay. While entropy indeed leads to the inevitable breakdown of systems, it also fosters new forms of order and complexity. Consider the way life emerged on Earth. The transition from simple molecules to complex life forms, the rise of ecosystems, and the development of intricate biological processes. These are all outcomes of the very processes of entropy. As energy flows through a system, it allows the creation of more complex structures, as long as there's a consistent input of energy to sustain these structures. Life, in this sense, can be viewed as a temporary, localized reduction of entropy, a dynamic process that resists the overwhelming forces of disorder by maintaining and evolving complex systems. Life can be seen as a defiance of entropy's ultimate goal, though this defiance is always temporary. Life's complexity is born out of the very forces that drive the universe toward its eventual state of maximum entropy. But this temporary victory over entropy is always fleeting. At some point, every system will reach a point where it can no longer sustain itself. A human body, for example, will eventually experience the breakdown of its cells, the failure of its organs, and the cessation of life. Similarly, stars burn through their fuel, and eventually, they collapse into black holes or explode as supernovae. This inevitable progression is a direct consequence of the second law of thermodynamics, which tells us that entropy will always increase, and systems will always tend toward a state of greater disorder. Yet this inevitability doesn't necessarily make the process of life, of growth, and of change less valuable. If anything, the knowledge that everything is in a constant state of flux heightens the preciousness of our experiences and the importance of the choices we make. The human experience itself is a fascinating interaction with entropy. While we cannot escape its influence, we continuously work against it, constantly trying to maintain order in our lives. This struggle manifests in countless ways, from the way we organize our homes, to the way we build societies, to the way we care for our health. We find comfort in structure, in predictability, in the maintenance of order. Yet we are constantly reminded that entropy will always prevail in the end, that nothing lasts forever. This awareness of impermanence compels us to create meaning in our lives, to cherish fleeting moments, and to understand that our time is limited. Interestingly, the very idea of time itself is also deeply tied to entropy. While we experience time as a steady flow from past to present to future, the reality of time is more complex. The passage of time, as we perceive it, is linked to the increase of entropy in the universe. In fact, the second law of thermodynamics not only explains the forward progression of time but also gives us a way to distinguish between the past and the future. Imagine a universe where entropy remained constant. In such a scenario, there would be no observable difference between past and future, and time itself would lose its directional quality. It's the increase in entropy that provides the arrow of time, giving it a distinct direction and making the future different from the past. As we consider this, we must also recognize that while entropy is a universal force, its effects are not uniform. Different systems experience entropy in different ways, and the rate at which entropy increases can vary depending on the specific circumstances. Some systems, like stars, undergo a rapid increase in entropy as they burn through their fuel and collapse. Others, like the human brain, experience a much slower progression of entropy, but the effects are nonetheless inevitable. Similarly, in the broader context of the universe, entropy manifests itself in various forms, some of which we observe on the smallest scales of particle physics, and others on the grandest scales of cosmology. One of the most intriguing aspects of entropy is its connection to the future of the universe itself. As the universe continues to age, it will inevitably move toward a state of maximum entropy, a state where no more work can be done and all energy is uniformly distributed. This is often referred to as the heat death of the universe, where all thermodynamic processes cease. While this future may seem distant, it's a fundamental aspect of the laws of physics, and it shapes our understanding of the ultimate fate of everything in existence. The notion of a heat death, however, is not a nihilistic one. It serves as a reminder of the deep interconnectedness of the universe and the inexorable forces that govern all aspects of reality. Yet, even in the face of this eventual heat death, entropy doesn't simply represent an end. It's also the creative force behind the very structures that define our universe. The formation of galaxies, the birth of stars, the emergence of life, these are all outcomes of the dynamic interplay between order and disorder, energy and entropy. Even as systems decay and break down, they create new opportunities for further evolution and change. In this way, entropy is not just a force of destruction, it's also a force of transformation, of renewal. The question of whether life can be sustained in the far future, when the universe has reached a state of maximum entropy, is a fascinating one. In such a scenario, when energy is spread uniformly and all thermodynamic processes have ceased, the universe will be devoid of any meaningful structure or organization. Life, as we know it, would no longer be possible. And yet, the drive to understand entropy, to probe its deepest mysteries, continues. Scientists, philosophers, and thinkers of all kinds are exploring ways in which we might avoid, delay, or even understand better this fate. Can we manipulate entropy in ways that allow life to persist in a universe that seems destined for decay? Or is entropy truly the ultimate arbiter of fate, one that no force can defy? In many ways, our relationship with entropy speaks to the human condition itself. We are creatures caught in the flow of time, experiencing the gradual increase in disorder as we age, as the world around us changes, and as civilizations rise and fall. But at the same time, we are also creators, constantly finding ways to resist entropy, to build, to grow, and to preserve. Whether through art, science, technology, or the simple act of caring for one another, humans have a unique capacity to create order from chaos. This ability to impose meaning and structure on the world, even in the face of inevitable decay, is one of the most defining features of human existence. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.